समुद्रवसने देवी पर्वतस्तनमण्डले विष्णुपत्न्यै नमस्तुभ्यं पादस्पर्शं क्षमस्व मे. Those who dare to fly don't care to leave their footprints behind. Welcome to FVS. A very good morning to all of you. Are you able to see my screen?
Yes.
Okay.
Yes, sir.
Thank you. So let's start with 2D theory, state of the art, in parallel to the 1D theory, state of the art that we did last time. But before we get to that, we will have some winding comments about the 1D theory, especially an even better approach by removing the displacement and rotation variables, what we call as the fully intrinsic formulation. As far as the 2D theory is concerned, the reason why it's important is, as we have seen, there are many shells or plate-like structures which are part of flight vehicles, like the cover skin of the fuselage, of cover skin of the wing, of the tails, a helicopter fuselage, or space vehicles, launch vehicles. All of these have thin shell-like structures, and in smaller dimensions, their curvatures are fairly small when you're looking at them as panels. So you could even treat them as plates in many cases if the curvature is not very large, or in other words, the radius of curvature is very large. Extremely sorry for the delay. How many of you are there are still around? Okay, thanks. So in any case, I think for those who are missing out, they will have the access to the video recording. So this is a very important class. So do convey to the other students that they need to watch this video, because this is very critical from this entire course point of view, because it's a culmination of whatever we have done in the previous 25 classes. So this 26th class is the culmination of that, and it's a kind of a summary as well as the main takeaway from this entire course. And we really needed to do all that we did in the previous 25 classes in order to get to a stage where we are at right now, in order to appreciate what is the takeaway and how we can actually utilize it, irrespective of whether we are structural engineers or regular flight vehicle engineers of any other kind. I had just begun the previous class where we talked about the 2D theory. Most of today's class will be dealing with that, so that we are having the capability to deal with cover skins. We are having the capability to deal with shells in general, another example being the spar web, etc. But this 2D theory, we will juxtapose or sandwich between the 1D theory and the 3D theory, 2 being the mean of 1 and 3. So we will start off by reviewing what we have said about the 1D theory, and then we will end today's class by looking at the 3D theory of elasticity, and in between we will look at the 2D theory, so that just by watching today's lecture video you can get the entire picture of the current state of the art in flight vehicle structures and how to approach any problems related to analysis or design in this particular arena. Yeah, so this is something that we already did in the previous class, so I'll go through it quickly. The 1D loads are small f and small m, and recollect that all the variables, unless otherwise mentioned, are basically column matrices. 3x1 column matrices, each element corresponding to the directions x1, x2 and x3, and they're all obtained from the corresponding vectors by dotting them with the big BI system, which is the unit vector system, Cartesian coordinate unit vector system in the deformed configuration. So every one of them is that, except small f and small m, which are in the small b system if you're having conservative forces. But if you're having non-conservative forces, for example follower forces, like what happens with let's say a missile or a launch vehicle, when the thrust which is coming out of that rocket engine is actually parallel to the axis of the engine. So, and also in fighter aircraft, when you're doing thrust vectoring, for example, the thrust, so that's basically a follower force. That, in other words, as the structure deforms, the direction of the force also changes, the thrust force. So we are having the capability of handling those as well, for especially for flight vehicle structure designs for space. But in general, the follower force, or forces which change direction, by forces we mean general, in a generalized sense, that could be moments as well, which change direction with the deformation as the load increases. So this is basically what is the capability which is built into it. So in this case, we have small f having the components small f1, small f2, small f3, and small m has the components small m1, m2 and m3, where f1 of course is your axial force distribution per unit length of the beam. Similarly, F2 and F3 are the transverse force distributions per unit length, and similarly your M1 is the torque per unit length, and M2 and M3 are the bending moments, applied bending moments per unit length. So all of these F1, F2, F3, M1, M2, M3 are given in the analysis problem, especially from the aerodynamics, but also from the weights and other aspects in terms of the distribution on an aircraft wing or in the fuselage or in the tail. And whatever you have in your, for example, the textbook that we have been following, the CT Sun, is actually contained within this particular slide. So, for example, if you're talking of small f1, let me use a okay, so if you're using small f1, are you able to see my writing now? Yeah. Okay. Okay. So small f1 is basically your axial force per unit length, and this is covered so this is basically your geometrically exact beam theory that we have already discussed, and we will review in today's beginning of today's class. So your f1 is a distributed force. Similarly, there could be a concentrated force as well, which is f1 hat, which is at any particular location anywhere between x1 equal to 0 to L. So x1 star is at particular location between 0 to L, and there could be many such f1 stars at various values of x1 star where the concentrated loads could be mentioned. But recognize that in reality there's no such thing as a concentrated force or a concentrated moment, because if you had one, that could cause infinite stresses stresses, and you know that the material cannot hold stresses beyond its own failure limit, yielding and or ultimate, and so therefore it is absolutely makes no sense to have concentrated forces, because the boundary condition at those locations would say that the stress is infinite. So in reality, what actually happens with concentrated forces is actually they are distributed over a very small area. It's just that the area over which those forces are distributed are very small. In other words, they are also actually the small F1 only, but they are acting over a very small area. In other words, F1 value is, which is per unit length, is very, very large. So that's all that it means. But in case we need to work with a problem where it is something is prescribed as a concentrated force, it comes as boundary conditions through this F1 hat star. So now this is as far as the geometrically exact beam theory variables are concerned. On the other hand, if you're looking at your textbook, that is CT Sun, that many of you might have referred to, all that we are doing, if we take only small f1 and keep all the others zero, that is f2, f3, m1, m2 and m3, the applied loads per unit length, and the corresponding reactions that might be there in those respective concentrated forces that you could have at the again at x1 star, all of them. So you would have f3 star, f3 hat at x1 star. Similarly, your capital M1 hat, which is a moment, which is a torque applied at a particular location in a concentrated sense. You could have M2 hat, M3 hat, etc. at various values of discrete values of x1 star, or where x1 star could be anywhere between 0 to L, including 0 and L if there are tip forces or forces at either one of the ends. Now, all that we are saying is that if you look at CT Sun in terms of its chapters and or sections, then whatever is covered in your textbook as chapter 2 and also as chapters sections 7.1 to 7.6 is, and all that we are doing is taking only f1 or f1 hat and setting all the others to 0. So it's a special case. So that's how you have to look at it. So that's the significance of what we have produced on a single slide, that we will review again once we complete this particular exercise. So similarly, if you're looking at F2 and F3, both have a very, very similar connotation. They are basically transverse loadings. So whereas in the case, if you draw, let's say, a beam like this, this is basically you're talking about your F1 hat as a concentrated load at, let's say, x1 equal to L at particular location, whereas you have it in a distributed sense, varying as a function. So that is basically your F1 of x. So now if you're taking only these two into account, and again you could have at various other locations also your F1 hat at some other x1 star concentrated axial load. So when you have only these, that's what is basically covered in your chapter 2 and also chapters 7.1 to 7.6, which actually deals with elastic stability or buckling. So all that you have is that your F1 hat is negative, or your F1 is negative, so that you do not have tensile loading, you have a compressive loading in some sense, that if small f1 only, if it is there, it is changing sign in such a way that at the left end it is moving towards the interior of the beam, and at the right end it's moving, changing sign and moving towards the interior of the beam again. So that's basically creating a compressive load. So and buckling could be either global buckling at the entire beam level, or it could be local buckling, what is called as wrinkling or crippling as well. So all of these are contained within this particular model. So that's the important thing. Now if we come to F2 and F3, Both of these are what we call as these concentrated loads. So for example, this could be your F3 hat if this is, let's say, the X3 direction. So that would be F3 hat at a particular value of X1 star. Similarly, if you have a distributed load, so then you would have, suppose you had a distributed load, something like this, then that's what you call as your F3 of X1. Okay, it's a distributed load per unit length. And it could be there throughout the beam, or it could be in parts. So you can define it in the appropriate way in the entire domain of X1 equal to 0 to L. So that is, so F2 and F3 are in just two perpendicular directions, but both are transverse directions as far as the beam is concerned. So their behavior is very similar. So where does this come in your textbook? All that you have to do in your general equations that we have just shown, you have to set only F2 or F3, or if both are present, both of them, and set all the others, F1, M1, small m2, M3, and the hatted quantities to 0. Then you would get what is actually given to you in your chapters, sections rather, 4.3, 4.4, 4.5, and also the entire chapter 5. So this is basically covered over there. So where you're talking about transverse forces, which are basically essentially shear forces, and what is the result of them. But there is also another way through which these same transverse shear stresses are coming, and that's through torsion, and that's what is covered in chapter 3 over here. So if you have only small m1 and or your m1 hats at various locations along the beam, then your entire chapter of 3 is a special case of this particular equation that we are dealing with right now. Similarly, if you're looking at M2 and M3, they are nothing but the bending that you're applying, and if it's M2 hat or M3 hat, it is not distributed but concentrated at certain locations. So these are covered in what you see as 4.1 and 4.2. Equivalently, you call it as flexure or bending. It means one and the same. You're basically having a flexible curvature, as I was explaining to one of the students who was asking about flexure in particular. So that's basically covered in your 4.1 and 4.2 of the textbook. So that's your M1 and M2, and usually this gets coupled with that these two things, that is, you have your bending and transverse shear are essentially coupled, because when you have a transverse force, that will also create bending, and therefore that's the reason why you see part of it coming in, part of fourth chapter coming here, and the second half of the fourth chapter and the following fifth chapter coming over here. So finally, that's as far as that covers this entire geometrically exact beam theory, all these chapters. Now, if we look at what we are going to do today, it is basically geometrically exact plate theory, but it can be generalized to a geometrically exact shell theory as well, where initial curvatures are introduced. Just like a beam becomes an arch when you have initial curvature, but we are talking about beam in a generalized sense, so we include initial curvatures there. Similarly, next, if you talk about the geometrically exact shell theory that we are going to discuss today, that's also going to cover certain parts of your book. So that's basically your section 210, your section 7.7, 7.8, 8, the entire chapter of 8. All of these can be thought of as special cases of what we are going to cover today in geometrically exact shell theory. So in other words, it's really not worth spending so much time reading all these sections and chapters. Everything, in fact, in a even more generalized sense, is covered in these two state-of-the-art theories, the geometrically exact beam theory and the geometrically exact shell theory. Now, let's also look at it in a diagrammatic sense of the beam theory so that we can understand the shell theory a little better, because shell theory is a little complex to understand, and that's why I'm bringing back the beam theory, so that if you understand that, then you would understand this in a much easier fashion. So that's the whole idea of revisiting the beam theory over here. And so all that you had is your inputs, which are the loads which are given to you, which is in terms of, let us say, your F, which is again a column matrix. Then you had your F hat, which is also a column matrix at various locations along X star. So these are the distributed forces and so-called concentrated forces, because I'm saying so-called because they don't exist in reality. It's just that very large values of small f are idealized as f hat, but it's not necessary. In our model, we can actually take them the way they are. For example, the way the aircraft engine is attached to the wing, there is many people will idealize it as a concentrated force, but actually the way the pylon and nacelle structure is and how it is actually joined will show that it's actually a finite contact area over which the engine is attached to the wing. So it's actually a distributed load that both the thrust as well as the weight of the engine are exerting over there, and can actually be taken as large values of small f over there, rather than as f hat. You would get a much more closer to reality approximation. If you put it as a concentrated force, you end up creating infinite stresses which are unreasonable. But of course, there are ways of overcoming that through additional assumptions. It's basically like when you say a lie, in order to protect yourself, you need to say more lies in order to cover up the first lie. So essentially, that's basically what you're doing when you make irrelevant, unnecessary assumptions. You want to cover it up and or make changes in order to come back to what the reality is, or at least closer to what the reality is. So if you cook something without salt, you again add a little more salt to kind of repair it to make it edible. So that's essentially what it is. So in addition to that, we have the distributed moments, torques as well as the applied bending moments, and then you have the similar ones in a concentrated sense. So essentially these are the inputs in terms of the loads, the entire set of inputs that you could have in terms of the loads. Some of these f hats and m hats could either be considered, as I said, as very large small and f and m, or small f and small m, or they can be considered as boundary conditions depending upon how you want to approach the problem. So now there is an effect of this in terms of how the structure reacts. See, that's the basic difference between a non-living thing like a structure and a human being who can respond rather than react. Once you react, you have to have your Newton's third law kicking in. Every action is equal and opposite to has an equal and opposite reaction. So that's basically the law of karma. So what does this set of loads result in? They result in your F and F hat. The direct effect is your F, which is the section force, which includes the axial force, which you plot typically in an axial force diagram, and the two shear forces, which you plot in shear force diagrams along x2 and x3 directions. So that's your F1, F2, F3. We are writing it as a column matrix. So all variables that I'll be writing now are all column matrices, 3x1 column matrices, unless I say so, otherwise. So but this F can also be caused by small m and small m hat if there is a appropriate coupling over there. But the direct effect is from small f and big F hat, which are causing this reaction from a particular cross section of the beam, how it is going to react to that through axial forces and shear forces. Similarly, your m and m hat are going to be small m and big M hat are going to be reacted by your reactions, which are your big M, which is M1 being the torque and M2 and M3 being the bending moments at the cross section. So essentially they are integrations of the stresses with the appropriate lever arms. Your F also, F1, what is it essentially? It is nothing but your F1, for example, is nothing but an integral over the cross-sectional area So let me put a double integral over there. So integral over the cross-sectional area of your sigma 11 dA. So similarly, your F2 is again going to be an integration on the cross-sectional area of, can anyone guess what is the stress that we are integrating over there? Which 3D stress when integrated gives you the shear force F2? Anybody? See, yeah, which particular? Very good, yeah. So it's tau 12, correct, Samanvai? So it's basically because it's acting on the one phase, because that's the cross-sectional phase, and you have to integrate the forces or stresses which are acting in the x2 direction to get F2. So that's basically what that is. And similarly, your F3 would be an integral over the cross-sectional area of tau 13. And similarly, your M1, M2, M3 are going to be just that multiplied by the distance from the either the center of twist in the case of M1 or the distance from the neutral axis in the case of M2 and M3. So all that you're going to have is the same thing, but you're going to multiply this. You're going to live by the leverage arm from either the center of twist or from the neutral axis. Then you end up getting your M1, M2 and M3. So these are the reactions which are coming. So just using a different color to distinguish them. But this would be enough if you had a statics problem. But you typically have a dynamics problem in flight vehicles because these are moving structures and they are vibrating. There could be an impact. There could be cyclic loading and various other possibilities because of which things vary with respect to time as well. So essentially, the reaction is coming not only in a static sense, but in a dynamic sense also. And that reaction is what we are calling as your P and H, the momenta. So P are the translational momenta and H are the angular momenta. And both are reactions. So essentially, your H is the direct fallout of small m and m hat being functions of time. Therefore, you are ending up with H. But there could be couplings as well. Similarly, because small f and small f hat are functions of time, therefore you end up with P. Otherwise, there could be a free vibration also. There could be no load which is acting, but you want to understand the material characteristics from a free vibration point of view. What are its natural frequencies? What are its natural mode shapes? So that helps you in understanding more complicated dynamics problems easily. So in that case, also you would end up with these P and H, that is the translational momenta and the angular momenta. Now, this is one level. So this is basically the structure at a cross-sectional level which is reacting to that. So F and M, what are the units for them? So this is basically in newtons, that's your axial force and the shear forces, and your M, which is in Newton meter, which is basically either the torsional or bending moment resistances offered by the cross-section to the applied loads. Now, on the other hand, the P and H are per unit length. So that is the translational momentum. Momentum, of course, is in kilogram meter per second, but then it's per meter that you're basically doing. So that's essentially what's happening over there. Similarly, your angular momentum as well. All of these you can actually see by just saying that the rate of change of momentum is going to give you your force, or the rate of change of your angular momentum is going to give you your moment. So that's essentially what that is. So let me just for space remove this. what is the next level? So we have already looked at two sets of variables that we have looked at, which is the loads and the stresses, or rather stress resultants, because it's a 1D problem that we are dealing with. Now, so you can see that by that correlation that we did by defining F with respect to F1, F2, F3 with respect to the stresses sigma 1, sigma 1, 2, sigma 1, 3, and similarly the M1, M2, M3 can also be defined with respect to them along with the weightages of the distance. So you can see that these are essentially related to those stresses but integrated over the cross section. So in other words, they are stress resultants at that particular cross section. Similarly, your P and H are momenta per unit length of the cross section. So then you go on to the next level, which is what has happened here in going from the inner circle to the outer circle is you have had the equilibrium equation setting in. So in other words, all of these, whatever we have written over there, are essentially the equilibrium equations, which is so the equilibrium equations are those arrows that are shown over there. So all these are basically equilibrium equations which are taking you from the small f and small m to the big F, big M, P and H. Okay, so then you're having the next level, which is you're now inducing the or invoking the constitutive law. So when you invoke the constitutive law, what happens? The direct effect of F is in terms of giving you your gamma. And gamma is again a column matrix which involves gamma 1, 1, 2 gamma 1, 2 and 2 gamma 1, 3, where gamma 1, 1 is your extensional strain of the reference line, not of the at a particular point, but of the entire reference line as an average. So that's gamma 1, 1. Then you have the other two elements of this gamma matrix, column matrix, as 2 gamma 1, 2 and 2 gamma 1, 3, which are nothing but your transverse shear strains. Okay, ignored in many cases, but if you want to deal with short and stubby beams, like for example, you might ignore it in the first case as far as the wing is concerned, but if you look at the tail, they are relatively shorter and stubbier, and so you might have to deal with transverse shear more importantly over there. So essentially, even you can do without that by including it in the warping, but if you want to do it explicitly also, it is possible. So that's the explicit way is what I'm discussing over here. So that's the first effect of F in terms of gamma. Then the other effect is M leading to the curvatures kappa. So kappa 1, kappa 2 and kappa 3, where kappa 1 is the twist per unit length, and kappa 2 and kappa 3 are your bending curvatures about the x2 axis and about the x3 axis. So that's your kappa 1, kappa 2, kappa 3 put together as a column matrix over there. Similarly, your P is going to result, because of the constitutive law again, in a dynamic sense, in terms of your velocity of the cross-sectional reference point. That is the intersection of the reference curve with the reference cross-section. That particular point is having a velocity v1, v2, v3, which of course changes as the reference cross-section changes along x1. So in other words, just like gamma and kappa, your v is also a function of x1. All the variables, unless otherwise said, not only are 3x1 column matrices, but they're all functions of only one spatial direction x1, and which is why they're called 1D variables. But this being a dynamics problem, it's still resulting in partial differential equations because time is another independent variable that we are dealing with. Now, as far as H is concerned, what is the main effect of that? That is your angular velocity big omega. And big V and big omega, we are distinguishing from the small v and small omega, which are contained within this big V and big omega. That small v and small omega are nothing but the vehicle's speed at the CG and the vehicle's angular velocity because of rolling, pitching and or yawing. So that's the next level. So how do we get from the F, M, P and H to the gamma, kappa, V and omega? What is that particular relation? That is your constitutive relation. So all this So whereas the previous one was the equilibrium equation, these equations, the red arrows, are nothing but your constitutive law. So all of them are the constitutive law. So then you have one more level that you're going to, which is basically your V and gamma are heading towards a quantity called u, once again small u, which is a function of x1 and time, which is nothing but the distance by which the points on the reference curve in the undeformed configuration have moved to the deformed configuration at a particular instant of time. So u is also a function of x1 and time. So this is the displacement. And how do you go from u to v? All that you have to do is to take a derivative with respect to time, which we will denote by dot. And how do you go from u to gamma? You are basically taking a derivative with respect to x1. Those are the two variables that they depend upon, time and the coordinate along the beam reference curve, and which we will denote any derivative with respect to x1 in the respect to the frame A, we will call it as prime. So as I said, any derivative of a vector or a tensor in general, except for scalars, you have to indicate that which frame you're taking the derivative in, because depending on the frame with respect to which you're taking the time derivative or spatial derivative, the value will change. So in all of these cases, unless otherwise said, it is basically with respect to A, that the frame A, that is the aircraft fixed reference frame, that we are taking these derivatives. So that's how you move from U to V and gamma. Similarly, the variable which is going to affect your kappa and omega is the displacement, or a variable generalized sense, which is nothing but your rotation. So that theta, when you are taking time derivatives, you're ending up with omega, and that theta, when you're taking spatial derivatives, you're ending up with kappa. So this is the entire bigger picture, where you're going from that inner circle of the applied loads to the external circle of how the structure is responding as a whole. And in doing that, it is basically going through three steps. One is the equilibrium equations, then the constitutive law, and what we have finally written here, which is nothing but the kinematics. So the kinematics are the ones which relate u and theta with v, gamma, kappa and big omega. So that relationship is what we are calling as the kinematics. So this, if you understand at the 1D, which is very, very simple to understand and also very computationally efficient to implement, but most difficult to derive. So you have to understand this, because here you are involving a dimensional reduction from a 3D model that you're starting with, 3D elasticity, strain energy per unit volume. You have to integrate over the cross section, and on the cross-sectional analysis, things are going to depend on two coordinates, x2 and x3. So everything is going to be a partial differential equation when you're trying to solve over there and bring it eventually to a one-dimensional system. So getting to a beam theory which is exact, which is what we have listed out in that slide, is a difficult task. But once you get there, applying it is the simplest, understanding it is the simplest. So that's the reason why we started with the beam theory, because anyway we are not doing the derivations, but we are only presenting the final results, and therefore the final results are those which are the simplest to understand. Once you understand this particular concept, it's very easy to understand your 2D theory. So that's the reason why the 1D theory was discussed even before the 2D theory. And even if you look at your book, you are basically dealing with chapters 2, 3, 4 are all dealing with 1D model, which is essentially your axial forces, your bending moments, the torques, and the transverse shear forces, and the stresses and stress flows which are resulting because of that. So let me get back to, I don't know if you're able to see my slide again. I think there is some issue. Okay, takes a little while. Okay, so now So let's revisit this. So you have a small f and small m as your 1D loads. You have your stresses, big F, big M, and in a dynamic sense, the 1D stresses include P and M as well, the momenta. Then you have your strains, which we just saw, gamma, kappa, and in a dynamic sense, the velocity of the reference line and the points on the reference line, and the angular velocity, which is of the cross section at different locations along the reference line. And eventually your displacement field, u1, u2, u3 along the same cross-sectional coordinates, again functions of x1 and time, and which is basically taking you from the reference curve in the undeformed configuration small r to your big R. So essentially there's going to be a rotation from the small b system to the big B system, and that involves what is known as a direction cosine matrix Cij, which is just got by dotting these quantities. Now the direction cosine matrix, by the very name, you can see that cosines are involved, or cos thetas are involved, because theta 1, theta 2, theta 3 are the actual deformation, and that is expressed in terms of cosines over here. This is one way of expressing it, but whatever the way of expressing that, that is always going to create a problem, that theta and the direction cosine, or in terms of so-called Euler parameters, Rodriguez parameters, etc., which are alternate ways of dealing with rotation, which you will encounter in future courses. So irrespective of that, these bring in additional complications, especially in terms of the levels of nonlinearity, because very soon we will see that without them, all the highest levels of nonlinearity that you're going to have is only quadratic. So it's only one step above linear that we are going to get even a geometrically exact beam theory. But once we have a situation where we have to deal with these rotations, the nonlinearity level jumps from 2 to infinity. So is there a way of avoiding that, is what we will see as the new thing for the 1D theory today, other than what we have already covered in the previous class. So the 1D equilibrium equations are relating your small f and small m to your big F and big M. In addition, you will also have the dynamic terms on the right hand side. In addition to these governing differential equations, you will also have a set of boundary conditions which are going to specify your f1 hat and m1 hat at various values of x1 star, including perhaps at x1 equal to 0 and L. Okay, you may or may not have all of the elements of a particular column matrix expressed. For example, f1 hat might be mentioned, but not f2 hat and f3 hat, or the other way around, and so on and so forth, but at a particular location. For example, the simplest example is a simple support. We are going to consider, or rather in the aircraft industry to start with, you consider the fuselage as a simple supported beam, simply supported beam with a overhang. So at these simple supports, you will have the displacement equal to 0 with respect to the support, but you will have the rotation which is possible because it's a hinge-like scenario, and therefore what you have to specify is the moment, and what is the moment which is transferring from the wing to that particular thing will become the applied moment at that particular location. So you have one condition at certain types of boundaries, you will have a mixed kind of boundary condition, some which are in terms of the displacement field generalized, and some which are in terms of the force field again generalized. When I say generalized displacement, it means includes rotation. When I say generalized forces, it includes moments. So now let's look at the form purely from a mathematical point of view. What kind of equations these are? These are differential equations, because you have derivatives with respect to x1 which are indicated by primes on the left hand side. All these primes that you see over here and over here, and then you have the dots on the right hand side, over the P and over the H over here. So that's all there is. That is, these are first order differential equations, but partial, because you have both primes and dots, that is two independent variables. But if you have a statics problem, it becomes a first order ordinary differential equation. An entire right hand side will go to 0 of these two equations, and that's what most of what is covered in your book is. Whereas this is a much more extended version where you are having all kinds of dynamics which are possible, including structural dynamics, aeroelasticity, and what have you. all of which, those aerodynamic forces, etc., how they are going to vary with the time, and will all be contained in your small f and small m, and how they vary with x1 and how they vary with deformation, etc. All of this will be contained within that. But essentially what we are seeing is you have only the first derivative as the highest derivative, and therefore it's a first order differential equation set. So the first equation that we have written is actually a set of 3 scalar equations. The second equation is also a set of 3 scalar equations, because remember that all of these quantities are 3 by 1 column matrices. So essentially you are having a coupled set of 6 ordinary differential equations, all of which are first order. Now let's look at whether they are linear or non-linear. Now remember that it's not only big F and big M which are unknowns, not only big P and big H, but also your K, gamma, omega and V, big omega and big V, all of these are unknowns as well. So therefore you see that there are terms in which 2 unknowns are multiplying each other. So this is one example, this is another example, this is a third example, there's a fourth example over here, a fifth example over here, and a sixth example over here. But the fortunate thing is that none of these are beyond the quadratic linearity. So it's just 2 unknowns which are multiplying each other. So which is much easier to deal with than higher order non-linearities. So that's essentially what it is, and this would of course be a situation where you are not having a homogeneous equation, because you're having terms which are not derivatives as well, including the loads small f and small m, as well as all these quadratic terms which are essentially the unknown variables multiplying each other. So this is as far as the mathematical form of these equations are concerned. So essentially you are having a coupled problem which is initial and which is also having the boundary values, and these have to be substantiated with the corresponding initial conditions and boundary conditions. Siddharth, you have something to say? Okay. So then let's move on. So next is the constitutive law, gamma, kappa, P and H in terms of F, M, V and omega. So the only place where an approximation is coming is through these constitutive laws, and even there we are, because of the employment of the variational asymptotic method, we are getting asymptotically correct results. So the smallness of the cross-sectional dimension to the length has no bearing on the equilibrium equations or the kinematics. The bearing it has is only on the constitutive law, in particular the first set of equations that we have written here between gamma, kappa on the left hand side and F and M over here. So these values of R, S and T are going to be determined as in an asymptotically correct sense. So as and when this small parameter of cross-sectional dimension to the wavelength of the beam no longer is a small parameter, then this is the source of any problems that you're going to have. But then of course once that happens, obviously it's not a beam anymore, and you're not supposed to be using the beam theory. But there's a wide class of problems in flight vehicle structures and many other structural mechanics problems in other industries as well, where you can actually utilize this particular approximation of a beam, and using asymptotically correct results ensures that it is almost as close to the 3D results as is possible. Next, we have the kinematic equations, which are relating your gamma and kappa to your u and your theta through the C. That is basically your direction cosine matrix. Now, if you look at it, the constitutive laws are not even differential equations. They are just algebraic equations. And if it's a linear constitutive law, they're just a set of linear simultaneous equations between gamma and kappa on the one hand and F and M on the other hand. Similarly, the dynamic equations are between P and H on the one hand and between V and omega on the other hand. But if you have thin-walled problems, both open cross-section as well as closed cross-section, single cell as well as multi-cell. In all of those cases, if you want a more accurate result, you have to go for the next higher order approximation in your deriving your constitutive law, and your R, S and T that you see, the stiffness matrix over here, will no longer be a matrix of constants. It will become a matrix which is going to be functions of your gamma kappa or of your F and M, irrespective of the way you write it, in an inverted form or this particular form. So essentially you're moving away from constants. So in other words, the relationship between the strains and the stresses, or rather the resultant generalized 1D strains and the 1D stresses, are going to be nonlinear in nature in general, especially for flight vehicles, because we are going to extensively use thin wall structures like I sections, C sections, and many other kinds of sections, cruciform, etc., depending upon the particular design choices which are made. So the first set were ordinary differential equations for statics and partial differential equations for dynamics, that is the equilibrium equations. The constitutive law were all algebraic equations. The next set, the kinematics, is again differential equations, but if you are looking at each set separately, they are like ordinary differential equation, because the only derivative that is there in this particular equation is the prime, whereas the only derivative that is there in this particular equation is the dot. So in a sense, they are like ordinary differential equations, once again first order, because the highest derivative that is appearing with either with respect to x1 or in the first equation, or in the, with respect to time in the second equation, are both first derivatives. So these are first order ordinary differential equations. Again, they are nonlinear because of certain terms which are occurring, which is basically the C is containing the theta and in a cosine form. So they already within itself it is an infinite level of nonlinearity, and in turn it is multiplying u prime here and is multiplying k tilde times u over here. Your k tilde, of course, is small k over here, unlike the big k's that we are dealing with over here. So this is your initial twist and curvature to take care of arches and to take care of let's say any other curved initial curvatures or pre-twist, etc. So now you are basically having an infinite level of nonlinearity over here. Is there a way to overcome that, is what we will see as an alternative over here. Already what we have over here is a geometrically exact beam theory. But now we will move one step further and see if we can do away with this C forever, and not only C but also what C stands for, that is theta, and any other form of expressing theta like Rodriguez parameters or Euler parameters. That's what leads us to what is known as a fully intrinsic formulation, by which we mean something which doesn't need not only rotation variables but even displacement variables. So without displacement and rotation variables, we can solve this entire coupled problem. So that's where we move from a geometrically exact beam theory to a fully intrinsic geometrically exact beam theory, that is one level higher over there. So let me clear the pen markings. So what we do in the fully intrinsic formulation is there is no need for these kinematic equations anymore. Instead, we are going to introduce what are known as the relationship between your gamma, kappa, v and omega directly, without involving your u and c or theta. So that's u, c and theta will be eliminated from the problem. In other words, you'll no longer have any of these 1D deformations. You'll no longer have these two sets of equations, but you will have direct relation between your kappa, gamma on the one hand and your omega and v on the other hand. So these two can be related directly to each other, and a very simple manipulation is required in order to do that. What do? You take the time derivative of these two quantities. In other words, you take the dot of this and you take the spatial derivative of this, and then you eliminate between those two equations your c and u. So once you do that, you have a direct relationship between kappa and gamma dots with omega and v primes. So that's essentially what we'll do. Again, I'm not going into the derivation. We're just presenting to you the final results. So let's see what happens over here in the fully intrinsic formulation. So this is what happens. So when you relate the omega and v primes to your kappa and gamma dots from the previous two sets of equations, you end up with very simple straightforward equations that big omega prime is equal to kappa dot plus omega tilde k. So now you see that we have ended up with a first order differential equation, but it's a partial differential equation because it involves both a prime as well as a dot. But the beauty is that now we have a nonlinearity which is once again only up to quadratic, unlike the infinite level of nonlinearity which we had earlier because of C. Similarly, if you look at the second equation, which is relating v prime to gamma dot, that also you see that there are only maximum of first derivatives, which means it's a first order differential equation, but because both independent variables x1 and t are involved, it is a partial differential equation. But once again, as far as nonlinearity is concerned, the highest level that you have is a v tilde times k over here and an omega tilde times gamma over here, which both of which are quadratic nonlinearities. So that's the advantage of going to this system. Advantage of going to this system of fully intrinsic set of equations. So what is going to then happen? As I said, you're going to get rid of this 1D deformation and all of these equations which are no longer needed. So that's essentially what we are going to do. We are going to get rid of those equations and we are going to get rid of 1D deformation. So now we have only three sets of equations and three sets of variables that are involved. Load, stresses, strains are the variables, and your equilibrium, constitutive law, and kinematics are the only equations that you're going to deal with. So this is a set of equations which are both algebraic as well as, because of this, and differential equations, which are partial differential equations, first order partial differential equations, which involve initial conditions with respect to time and the boundary conditions with respect to x1. And so this is a system that you can solve for the very simple cases that are dealt with in your CT Sun in chapters 2, 3, 4. You can actually do a very, very straightforward derivation of these quantities and see that you can actually cross-verify their final results of almost all that they have presented over there. So then, okay, so with that I think I'm completing the 1D theory in the essence of how to understand the 2D theory. So if there are any questions on this, I'll be happy to answer. Otherwise, I'll move on to the 2D theory now. And this class is, as I already warned through my teaching assistants, going to be slightly longer. So if any of you have anything else to attend to, like lunch and or other classes, please feel free to leave. But the full recording will be made available to you by the end of the day today, so that you can watch that in your free time. So this will be an extended class, but you will have access to those videos. So those of you who are having other commitments, please feel free to leave so that we can you can catch up through the video later on. So especially those who are going to leave, if you have any questions, I would be happy to answer right now. Otherwise, we'll move on to the 2D model. Okay, looks like,
Sir,
yeah, go ahead.
can you explain the last part, omega tilde and the product of omega tilde and E1?
Okay.
What does, it signify?
Okay. So this is E1, as you know, is your 1, 0, 0, which we introduced in the previous class. So what it is saying is that the transverse shear strains are not going to be affecting the this particular relationship. It's only the first term in your omega tilde matrix that is going to be there, which is going to affect it. In other words, the first column of that particular matrix. So that's essentially what this particular thing is saying, that you do not involve E2 and E3. Because we are not going through the derivations, I can't tell you how the source of this is coming, but it's quite clear to see in terms of the practical significance of this, that your E2 and E3, which are basically cross-sectional directions, are not going to affect this particular way in which the angular velocity is going to be related to your translational velocity because of the way in which this particular problem is created. That is, you are reducing the cross-sectional dimension to a point and basically the beam into a curve or line. So therefore, what you're dealing with as the set of equations here, including those with the yellow background, the entire set of equations here are all 1D as far as the spatial variables are concerned. So there is a very different behavior with respect to x1 as opposed to the behaviors with respect to x2 and x3, and that's why you see only E1 coming into picture. And you will see the parallel when we go to the 2D theory and look at the 2D fully intrinsic equations as well. There you will not only have E1 playing a role, but E2 is also playing a role, because both the x1 and x2 directions for a shell are large directions. Like in a beam, x1 is the only large direction, x2 and x3 are the smaller domains. So that's the reason why you have only E1 playing a role. Another way of looking at it is this term E1 plus gamma coming together. So what is actually happening over there? So if you look at E1 plus gamma, all that you're having is this. If you take the entire bracketed term over there, all you're having is a 1 plus gamma 1 1 over there, and here you're just having, because these are zeros, that is not there, so it's you are only having gamma 1 2 and gamma 1 3, and because these are engineering shear strains, you're 2 gamma 1 2 and 2 gamma 1 3. So essentially what is happening with E1 plus gamma is that you're saying that as far as gamma 1 1 is concerned, already it had a particular location, and now because of the extension it's moving to different locations by a slight amount, which is your small gamma 1 1, which is taking it further. Now on the other hand, 2 gamma 1 2 and 2 gamma 1 3 are the transverse shear strains, which are the additional rotations that the cross section is taking. It didn't have a rotation in the undeformed configuration. Because the way the undeformed reference curve and the unit vector system B1, B2, B3 was introduced. So now, over and above the rigid body like rotations of the cross section with the reference curve, you have an additional rotation which makes it no longer perpendicular to the reference line. It is that additional rotation in this direction and in the other direction like this, which are your transverse shear strains. So there is nothing to start with. That's why you have the zeros. So that's why you see only E1, that is the first term, 1, and then zeros, because there's nothing to start with, whereas in the first case you already have something to start with as far as the location along the reference line, and then you are further adding something because of the extension that is happening. So is this clear? Because I can't explain it mathematically because we haven't done the derivation, but I'm trying to explain it from a physical and variable meaning point of view. Is that clear, Samanma?
Yes. Thank you, sir.
Okay. So let's move on to the 2D model. So we will once again do it exactly in the way we derived the, or rather we expressed the entire 1D model in the previous class. We will start with a flow chart, we will start with the kinematics, and then we will go into the set of equations in that chart that we just looked at for 1D, similar chart for the 2D. So now how is it going to happen over here? And this is again the most comprehensive model that you can have according to today's state of the art from all perspectives, whether it is a cross-sectional analysis in a constitutive law through the asymptotically correct results because of the employment of variation asymptotic method, or in the use of the geometrically exact plate or shell theories. Here I will describe the shell analysis, but going forward, to keep things tractable within a single slide, I will leave out initial curvatures, both twisting and bending curvatures, and deal with flat panels, which are nothing but plate models. But we can always extend it to initial curvature if we want. The methodology remains one and the same. So here, because it is a shell, not a plate, you have initial curvatures. You also have, like any structural problem, loads and boundary conditions. And then you have the geometry of the structure itself, that is the thickness of the shell, and whatever material it is made out of. If it's made out of multiple materials, the properties of relevant properties of all those materials. So these three become your inputs. So those which are with a green background, a peacock green kind of a background, are basically your input quantities, which are your initial curvatures, loads, boundary conditions, which are both the load boundary conditions as well as the geometric boundary conditions, where you specify the displacement or rotation at particular boundary edges, or in intermediate locations as well, if there is an intermediate support, like for example a propped cantilever or something like that, when considered as a plate or a shell model. So all of these are the inputs. Now we go on to the three set of analysis that we do, which are all expressed in a light blue background. So the light blue background that you see is a 1D analysis, a 2D analysis, and a recovery analysis. The 1D analysis, unlike in the case of a beam, which was along the larger dimension, the 1D analysis here, in the case of a plate or a shell, is basically along the thickness direction, which is a smaller dimension. So it's just getting interchanged. It's the same 3D problem, whether it's a beam or a shell, and in both cases it's breaking up into two parts, 1D plus 2D. But in the case of the beam, the 1D is larger and 2D is smaller. Here, in the case of a plate or a shell, it is vice versa. So always we do the smaller part first, because that whatever output comes out of it becomes an input for the larger part. So in the case of the beam, all that we did is the smaller part is a cross-sectional analysis, where we got the constitutive law, and then we use that constitutive law in the 1D analysis. Same here in the case of a plate or a shell. We are going to do the smaller thing first, that is the thickness direction, get the constitutive law for that. Now we are dealing with a reference surface or a reference plane, be if it is a shell or a plate respectively, and then for the analysis of that, the constitutive law that you derived through the thickness 1D analysis becomes the output of that becomes the input. So that is essentially what is happening over here. So now let's look at it. As an example, you could have, for example, a square or rectangular plate as shown over here, with any kinds of distributed loads that are shown on the top surface. They could have also on the edges. The edges could be supported in certain ways, and there could be intermediate supports as well of various kinds. So these could be lift distributions, drag distributions, and this could be either the entire wing or as a shell, or certain parts of it as a wing panel, in which case, many cases you can consider the initial curvature to be very small, and therefore, unless of course you're dealing with the leading edge, etc., where you do need to have this full shell analysis. Otherwise, you could do with a plate analysis in most locations, if you're dealing with just panels. So now that is essentially what you're doing. And once again, we will go from an undeformed configuration. Don't worry that this is small. You don't need to look at it, because I'm going to expand in the next slide and show it to you in an expanded form. This is just to put things in the perspective. So you're in an undeformed configuration to a deformed configuration. So even if you start with a plate, you might end up with a shell. So because there are curvatures that are coming up, but the distinction between plate and shell is essentially made in the undeformed configuration, not in the deformed configuration, because in the deformed configuration everything will have in general initial curvatures and therefore will look like a shell. So now what are these inputs going into? As I said, the first thing is always done with respect to the smaller dimension. First thing is always done with respect to the smaller dimension, and that in this case is one dimensional through the thickness, and that in general can be a nonlinear analysis. Just like I said, the cross-sectional analysis for thin-walled beams, be it open or closed cross-sections, can be a nonlinear thing. In other words, your constitutive law may not be linear algebraic equations, so a set of simultaneous equations, but it can be nonlinear as well. In other words, the stiffness matrix, the 1D stiffness matrix there, could be a function of the 1D strains. Similarly here, the 2D cross-section, 2D stiffness matrix, which is the stiffness matrix of the reference surface of a plate or a shell, will be a function, can be in general a function of the strains that are there in that particular reference surface of the it could be a mid surface, it could be a top surface, it could be the bottom surface, whatever you choose, the neutral surface, whatever you want to choose. But once you have chosen a reference surface, the initial curvature is going to be further augmented by the bending and the twisting. Similarly, your extensions in the two directions and in-plane shears that are going to happen, all of this are the 1D or the 2D strains that are there for the plate or shell. Now these 2D strains could affect the constitutive law. That's why in general this need not be a linear analysis. What is the special case of this nonlinear analysis? Is a linear analysis where you have, in a classical laminated plate theory that some of you are familiar with for composites, the ABBD matrix is a constant. So that is because we did a 1D linear analysis over there. The end result of that is the ABBD matrix, which is what we call as the 2D linear constitutive law. But here in general you could have a 2D non-linear constitutive law because those ABBD terms A11, A16, A26, etc. need not be constants. They can be functions. As the deformation increases, their values can change. So that is essentially what your 2D nonlinear constitutive law means. So that is only one result of this 1D nonlinear analysis. There is another result. Just like we had in the beam case also, we are going to get results for the warping, which is again a three-dimensional field. In the case of the beam, we said that what is warping? It's a three-dimensional field, which means that the cross-section is going to deform out of its plane and within its plane. Same here in the case of a shell, the through the thickness linear element, a normal element, is going to deform both along its length, increase or decrease its size, and it's going to deform from being a straight line to being a curve in both the directions. So this is basically again a three-dimensional warping field where the straight line, which was normal to the reference plane or reference surface, no longer is straight, but it is curved and also has changed its length. How much it has changed its length and how much at different locations and how much it has curved is all that warping basically contains. So the simplest plate theory is classical plate theory or classical laminated plate theory for composites, classical plate theory for metals, are basically those which ignore that warping and also bring in the Kirchhoff assumptions, Kirchhoff law assumptions that we talked about, the hypothesis, which says that just like in the case of a in the case of a beam, we said that plane cross section remains plane and remains perpendicular to the reference curve. Here what we are going to say is that the to the reference surface, any normal which is originally normal in the undeformed configuration remains normal and remains undeformed. So in other words, it remains straight and it remains perpendicular to that reference surface as the deformation takes place. So not only are we ignoring the warping, but we are ignoring the transverse shear strains as well, which are basically rotations of the normal over and above whatever rotations that the reference surface is undergoing at that particular location. So in other words, in reality, the normal no longer needs to remain normal, but if you assume it to be normal, then the transverse shear strains are ignored. So here we are allowing for everything to happen as it really does. So that's the reason why we end up with a three-dimensional field for warping and the strain recovery relations. So these are two outputs that you see for the 1D nonlinear analysis. Okay, what is the other thing that we have to do is the 2D nonlinear analysis. So this is along the larger dimension. This is equivalent to what you are doing with a beam reference curve. Now you have to do with a plate or shell, reference plane or a reference surface. Now that analysis along two large dimensions, namely in the case of a wing, for example, the chord direction and the span direction, as opposed to the thickness direction, which is the smaller dimension. So now, very rarely it is this problem is applied to the wing as a whole, as a shell. It's only the wing skin and the spar webs, etc., for which it is applied, where the thickness is really small compared to the other two dimensions. So what does the 2D nonlinear analysis do? It takes inputs from whatever you had already done, namely the 1D nonlinear analysis. In other words, this constitutive law is going to feed into this as the input. Without that, you can't do. Same way, in the case of the beam, we did the cross-section analysis, got the cross-sectional stiffness, and fed it into the analysis of the 1D beam, which is basically the reference curve analysis. Here we are doing the reference surface analysis by taking inputs from the through the thickness analysis, which has resulted in a constitutive law, the simplest example of which is the ABBD matrix for a composite. So now, once the nonlinear 2D analysis is done of the reference surface, once again you get an output which is nothing but your 2D displacements, strains and stresses. And the apart from the constitutive law, of course, you got an input from the load and boundary conditions, because depending upon that, your nonlinear analysis will change how much of deflection that is happening, the displacements, strains and stresses, all at the 2D level, by which we mean these quantities over here are functions only of x1 and x2 so far. To get the entire 3D field, we have to combine with what we had got earlier through the so-called recovery analysis. Only then we can get that. But before we get, and that would be the case as far as a linear model is concerned. But here remember that both of these are non-linear, the 1D as well as the 2D, which means certain iterations are required now, and that those iterations are the ones we will discuss now. Many of you would be familiar, if you have done nonlinear finite element analysis, that loads are increased in steps. You start with a smaller load and then you keep on increasing the load to the actual load, and that's basically what this particular loop is all about. So to start with, you don't go to the actual load, you give a small part of that load and then keep on adding to that to reach the actual load, and each time you have to check for convergence and whether the load step has ended, and if it has not, you continue this entire cycle until it has stopped. Now, in addition to this is a common thing that everybody does in any 2D nonlinear finite element analysis. Even if you're doing a 3D finite element analysis or a 1D finite element analysis, everybody does this particular thing to reach in steps the actual load. So this is one loop. But a new loop, which most people do not do, and which is actually very important, especially for flight vehicle structures, which are thin shells and thin plates, whether it's the cover skin or the spar web, they're all thin structures, and therefore nonlinearity here becomes important as well. So once this nonlinearity becomes important, you have another loop that we have to deal with, and that loop you see is over here. There is another loop that is happening, inner loop that is happening over here, where you're updating the constitutive law. Because if the constitutive law were constants, that is ABBD were constants, then just once would have been enough. But we know now that ABBD are going to be functions of the strains, the 2D strains, that is your epsilons and kappas, epsilons and rhos that we will discuss in the next slide. So those quantities are going to affect the ABBD values. So you start with epsilon and kappa equal to 0 to initiate the problem. You get one solution, and then this will give you the values of the 2D strains, epsilons and kappas, and then you substitute that in your ABBD expressions, and then you keep doing it, and usually this doesn't take more than 1 or 2 iterations. So this is but if you don't do it, it can create a very large error. But if you do it, it's not a very involved process because it converges so soon. It's just 1 or 2 iterations in the numerical iterations, it converges, and therefore it is important to take care of this in thin shells and thin plates. The extreme of that, of course, being a membrane. What is a membrane? Membrane is basically something in which the bending stiffness are negligible. Why is the bending stiffness negligible? Because the thickness is so small that it cannot offer any resistance to bending. It's not that the material is not at all stiff. It has a certain non-zero Young's modulus, but nonetheless, because the materials are not so far away from the reference surface or reference plane, it is not able to offer sufficient bending stiffness. So that's basically your membrane model. Same case, we could have degenerated the previous model, the beam model, to a cord or a string. So a string theory or a cord theory can be obtained as a special case as well from those equations that we already dealt with. All that you have to do is to look at a cross section which is essentially already very even smaller than what a typical beam is. So as you keep asymptotically reducing that to a smaller size, so essentially the leading term that you're going to have there is not going to have your bending affecting it. Same case in the case of the shell as well. So understand that there are two loops, one associated with the load, the other associated with the constitutive law because of the thinness of the shell or the plate, which is making the stiffness, the 2D stiffness, no longer constants but functions of the 2D strains. So this is essentially what you end up with. Once this whole thing is completed, both these loops are converged, the end result that you get out of this process is the 3D displacement, strains and stresses, because now you're going to apply the byproducts that you had of the 1D nonlinear analysis, namely the so-called warping expressions in terms of the 2D strains. Now, because of this converging, you now have the end results of the 2D strains, that is your 2D strains of epsilon and kappa are now found. They can be substituted in the warping, and therefore you recover all the 3D fields, that is the displacements, strains and stresses are all recovered. So this is again exactly parallel. If you have understood beam flow chart, the plate flow chart is just a flip-flop of the 1D analysis and the 2D analysis. So if you want to combine these two and say, all that you have to say is the smaller dimension has to be done first and then the larger dimension has to be done next. Whether it is 1D or 2D will get flipped depending upon whether it's a beam or a plate model. So this is the overall picture, so that you understand the bigger picture before we go on to the kinematics to understand the details of this particular movement from the undeformed configuration to the deformed configuration, which we will do on the next slide. Okay. Now here I would like to thank one of my postdoctoral fellows, Aditya Sabale, who I think about 4 or 5 years back he taught this particular class on my behalf, because I was on a international conference tour at that time, and he came up with this animation for this. So I'd like to thank him for that. It makes the understanding much better. But I don't know if the font size or thicknesses that he has used are good enough for you to see it. But nonetheless, I will have one more slide where I will have thicker lines so that it can be better understood in case you're not able to see some of the things over here. So what we have is to start with an undeformed state, which could be a shell in general, and a plate is a special case of that. So it has certain initial curvatures and initial twist, and then you have a deformed state. So just like we did in the case of the beam, we said that any arbitrary material point can have 3 displacements to move to a new location. We just break it up into parts. One, we say that it is getting a joyride on a cross section, as the cross section undergoes rigid body like motions, and the point also moves on it through 3 translations and through 3 rotations, and then the cross section further deforms into warping both out of plane and in plane, and that's essentially reaching the final position of that material point. Same thing over here, but instead of moving over, getting a joyride over a cross section, it is getting a joyride over a normal. So that normal to the reference surface is going to have 3 translations. It's going to have only 2 rotations, because a rotation of a line about its own axis is meaningless. That is what is called as a drilling degree of freedom, which is explicitly taken into account by certain theories known as Kosarat theory or director theories. But we will not deal with it right now because it's not essential. Even without that, we can get as accurate result as the 3D results, whether it is a theory of elasticity results or finite element analysis results or comparisons with experimental results or flight test results. So we can get that without that. So essentially, whereas a cross section has 3 degrees of freedom in translation and 3 degrees of freedom in rotation, totaling a 6. As far as a reference normal over here is concerned, it's a line, and a line can have 3 translations, fine, but it cannot have 3 rotations. It can have only 1 rotation about this, 1 rotation about this, but a rotation about itself is kind of meaningless. So because it is 0 thickness, that's what a line is by definition, and therefore any rotation about its own axis is going to be not going to contribute any strain. But there are ways in which that can be absorbed, and that's what I said is the so-called director or Kosarat theories, which we will not discuss over here. So now you're going to have, as before, an aircraft fixed reference frame. So because we are going to deal with the cover skin of the wing or of the fuselage or of the tail, we are going to see that it is these parts are on the moving aircraft, which is having its own velocity at its CG, and it's having a certain pitching, and it's having a certain roll, and it is having a certain yaw. So we need to take all of that motion into account. So we need to know how A moves in some inertial reference frame I, and this O could be the CG of the aircraft at which this coordinate system, which is fixed in the aircraft, is located. We could introduce unit vectors small a1, a2, a3 or corresponding to that. Now with respect to that, we want to see what is happening in terms of the change from the undeformed configuration to the deformed configuration over here. So let's go in steps. So first, like before, we introduce a unit vector system associated with the undeformed configuration, which is a Cartesian basis. You have x1 and x2 as the coordinates along the reference surface, and then you have x3 along the so-called normal that we are going to introduce. Therefore, corresponding to these 3 directions, the tangential directions have unit vectors which we call as B1 and B2, which are tangential to the surface, and B3, which is along the normal to the surface. And because it is a shell, that is, it is having certain initial curvature, both curvatures in the 2 directions in the normal sense, but also the twisting curvature if it is the case in some problems, which is the case in fact in most aerospace problems. So in general, all of these unit vectors will be functions of both x1 and x2. Now draw the parallel with what we said in the beam. B1, B2 and B3, the small B1, B2, B3 system were functions only of x1. Here they are functions of both x1 and x2 because those are the 2 larger dimensions about which the curvature can take place. So that's as far as small b1, b2, b3 are concerned. The next step is to introduce the normal. So that normal that you see over here has now been introduced about the b3 direction, and all the material points are at some location along that particular normal. So you first locate a particular point on the reference surface x1, x2, and then you go on the normal, either the positive or negative direction, to reach a particular value of x3 to reach any arbitrary material point within that shell. So then, so that point we will call as P. Okay, though it is shown at the end of that normal, it is not. It could be anywhere in the middle of that normal, also somewhere in between or on the reference surface. It's an arbitrary material point anywhere on that normal to the reference surface at a particular location x1 and x2. So now that point P, we want to see where it goes after deformation, because that is the point we want to follow, and then we want to see if that overall motion can be broken up into parts. One is a joyride with the normal, and then the warping of the normal. So again we introduce the position vector of the undeformed reference surface, which we call as small r of x1, x2. So that is from the origin, which could be the CG of the aircraft with respect to the aircraft fixed frame. So that is your R of x1, x2, which covers the entire surface of that undeformed configuration reference. So then we bring in an additional term to reach P, because with this R alone we can reach only those points which are on the reference surface, but there are points above and below the reference surface also, and therefore to reach them we need this coordinate x through x3. Ignore the dots over here, they don't mean anything, it's just a multiplication, because all these quantities that you're dealing with are just scalar multiplications, not the usual dot products that you have with vectors, because x3 is not a vector, therefore the dot doesn't have any meaning. So just ignore the dot. So x3 times b3 is what the distance you have to go along the normal to reach that particular point P. So the overall thing is the sum of this R and this x3 b3 is going to lead you to this particular point P, which is what we will see next. So that is your R hat. So now R hat is not only a function of x1 and x2 because of R, but also a function of x3 because you have gone along the normal to reach this arbitrary material point. That is your R hat. So again, you can go back to your beam kinematics that we discussed, and you can see the direct parallel that we are having over here in terms of the notations as well as the definitions. So from R to R hat. Next, we can write the expression for R hat as the sum of R along with your x3 into b3, which is a direct thing, very easy to see. Now we want to see what is happening to this P. You can see that it has moved by a translation along this direction, a translation along this direction, and a translation along this direction. So basically, essentially, you have three translations that the normal can get. So, which is very similar to what we were talking about in the beam case as well. So let's see what happens because of that. Now, essentially, that is going to result in a new location of the normal, which has moved through three translations and reached a particular new location over here. So once these three translations are performed, you have reached a new normal at the reference cross section, which may or may not remain normal to the new reference surface. But that displacement along the three directions is your translation u, which is going to be a function of x1 and x2, because the normal itself is located at different locations along the surface by choosing that particular point on the surface at which you want to draw the normal, which is your x1 and x2. So your u in the case of a beam was a function only of x1, the larger dimension. Here it's a function of x1 and x2 because both of them are larger dimensions. So that reference surface that you had in the undeformed configuration has moved to a new reference surface in the deformed configuration, and that motion, that translation is entirely governed by your u field, the 2D displacement field, u as a function of x1 and x2. So now that helps us locate this same reference cross section in the deformed configuration through a big R instead of the small r that you had earlier. So just like the small r, it is also a function only of x1 and x2 because we are going from one reference surface to the other reference surface, undeformed to deformed. So when you do that, you end up with this u adding up to this particular small r to get this big R. So in other words, this big R, as you can see through the vector addition, is nothing but a vector small r to this point, origin of the small b system, to an origin of what we will now introduce as the big B system, which is your u. So the small r plus small u should give you your big R, the position vector of the deformed reference configuration. So now what happens is, in addition to this translation, we will also have rotation of that normal. And therefore, your small b system has given way to a big B system over here. Once again, functions only of x1 and x2, which in general is different from the small b system because of the rotations of that normal. But actually there are only two rotations, as I already discussed. The rotation about the normal zone axis is meaningless unless you are dealing with a Koszart or director-based theory. So let's leave that aside for now. So now this new set of BIs, the uppercase BIs in the deformed configuration, just like in the case of beams, can be obtained from the small b system through a direction cosine matrix, which depends on those two rotations that you have had, theta 1 and theta 2, theta 3 being meaningless. So then once you do that, you have a possibility of locating that point P on the normal over here now by going a distance of x3 along the big B3 unit vector over here. So that is x3 times big B3 instead of x3 times small b3 that we did to locate that point. So far we are still not introduced the warping of the normal. So we are doing it in steps or stages because all of these displacements are commutative in nature. Whether you do this first and then that later doesn't matter. So you're basically adding up all of these in steps. So you first introduce the translation, then you introduce the rotation, but within the rotation the ordering matters. So there it's not commutative in nature. That is, a rotation first by theta 1 about b1 and then theta 2 about b2 is different from a theta 2 about b2 and then a theta 1 about b1. So there you have to be careful as far as that is concerned. But essentially we are containing all of that through this direction cosine matrix, so we are not breaking up our head over individual theta rotations over there. So now you have located that point x3b3 intermediately before the warping of the normal has happened. In other words, the normal no longer remains straight, it can become curved, and it need not remain a thickness h that it had earlier. The plate or shell had a thickness h. The normal also therefore had a length which is h, going from minus h by 2 value of x3 to plus h by 2 through the x3 equal to 0 at the mid surface, which if you have chosen as the reference surface. So that basically can have an extension or a contraction as well. So that is all going to be taken into account next. So now you see that it has become a reference curve like this instead of the normal that you had as a straight line over there. So that reference curve, you have the reference surface, and then now you have the reference normal breaking into a reference curve like that. Now the difference between that normal and the deformed normal is what is your warping, a three-dimensional field W1, W2 and W3. Now W1 and W2 are the ones which make the straight line into a curve, and W3 is the one which makes the straight line change its size, either increase in thickness or decrease in thickness. So that is the three-dimensional warping field that we have over here, which is Wi multiplied by big BI, which is going to give you from the normal that you have over here how much distance it has gone. So this normal is different from this normal because of the rotation of the small b system to the big B system. In addition, you are going to have this warping, which is seen over here as Wi times the big BI, an implied summation over I equal to 1 to 3. So now what is going to happen is that you can now locate that arbitrary material point which was at P originally at a particular location P hat through this particular vector r hat, analogous to the small r hat we had in the deformed configuration. So this big r hat is going to be made up of this big R and then whatever has happened because of this rotation and the warping that has occurred, which is essentially taking you from this point all the way to this point. That involves this particular vector wi times bi. So let's get to that. Okay, so now you see that your r hat is having a term which is r to locate the mid surface. That is because of only translations u. So this big R is equal to small r plus u. And then in addition, you have to move to locate that particular point x3. And now instead of along small b3, you have to move along the big b3. And then over and above that, the straight line is no longer a straight line, and it has changed its size also, because of which you have the 3 warpings along the 3 big B directions. So that's your total r hat. Whereas in the small r hat, you had only 2 terms to locate the reference surface and to locate a point along the normal. Here you are having also the reference surface, locating the point along the normal, and then the normal is no longer a normal. It becomes a curve and changes its size. Therefore, you are adding the warping over here. So then you bring in this equations over here to introduce the 2D fields. Just like we had the 1D strain fields in the case of a beam, which included the twist per unit length, the 2 bending curvatures, the extensional strain, and the 2 transverse shear strains, which are additional rotations. Similarly, here also we bring in the 2D strains, which involve both translational strains, which we will denote by gamma, and the rotational strains, which we will denote by k alpha, which includes not only the strains but also the initial curvatures. So we have to remove the initial curvature from this to get the actual elastic bending and or torsional curvatures. Now let's see what exactly is happening in these equations. Once again, if you go back to your beam equations, you will see a direct parallel over here. So now what would happen if there were no strains at all? Then the B alpha, that is B1 and B2, would be tangential to that surface. Just like your small b1, b2 were tangential to this surface, your big B also would have been tangential to the surface. So if there were no strains at all, these would have gone to 0. So you would have had r comma alpha is equal to B alpha. So where alpha takes on the values 1 and 2. So that's very easy to see. But now you do have a strain in the reference surface. It's not the same as what it was, and that is where the difference is coming because of the in-plane strains epsilon alpha beta along the b beta directions, that is the in-surface directions, and there's also a change happening in the normal direction, the b3 direction, because of the transverse shear strain. Now, the transverse shear strain in the case of a beam was the additional rotation that the cross-section had. Apart from the rotation along with the beam reference curve, it had an additional rotation which rendered it no longer orthogonal to the reference curve. Same here. Now you have the reference surface and the reference normal. It's getting a joyride on the reference surface, remains normal, but then additionally it can have its own rotation. That additional rotation that the normal can have over and above what it had with the reference surface is what is the transverse shear strains in this case. So these transverse shear strains are gamma 1,3 and gamma 2,3, and that's basically what you see along the big B3 direction, and that's why your r comma alpha is no longer B alpha. It's, in other words, B alphas are no longer tangential to the reference surface, but they have changed because of one, the in-plane strains epsilon 1,1, epsilon 2,2, epsilon 1,2, and also because of the transverse shear strains 2 gamma 1,3 and 2 gamma 2,3. So next we also see the curvatures. So your bi comma alpha, remember in the case of the beam, was just k cross bi. Now that K is having terms there, K1B1 plus K2B2 plus K3B3 in the case of the beam. Straightforward and simple. Here, there are two such quantities because now you have to take Bi derivative not only with respect to x1, which was the only large dimension in the beam, but here in the case of the plate or shell with respect to both x1 and x2. That's why comma alpha. So Bi comma alpha. Now Bi comma alpha, therefore you're going to have two sets of quantities there corresponding to alpha equal to 1 and 2, and that's where you introduce these curvatures, which are the twisting curvature and the bending curvature in these terms. And then in addition you have certain curvatures which do not appear in 3D elasticity but appear in what are known as micropolar theories. Reisner had an example of a micropolar theory, but again we'll not get into details of all of that. But if you want to do a 2D analysis properly, you do need to take into account these terms, which are going to have the B3 component as well, affecting how Bi changes with respect to alpha, and therefore these curvatures K alpha 3 are there as well. It's very easy to visualize what K11 is. It's basically a bending curvature like this. What K22 is a bending curvature like this. And what K12 is basically a twisting curvature like this. But your K13 and K23 are things that are associated with the rotations that are happening in these two directions, which are not very clearly visualizable. But if you go to micropolar theories, you can get, those of you who are interested in understanding it further can refer to Reisner's micropolar theory as well as micropolar theories by many other researchers as well. So that's the reason why you have this third entity, which in many people might ignore and just take as zero, which is why they get plate theory results or shell theory results very different from the 3D theory. One of the reasons. Many other reasons are there in terms of the additional approximations, assumptions that they make, but this is also one of the reasons why they get very erroneous results with 2D models. And the other thing which is also non-classical but is taken into account, for example, in a Reisner-Mindlin-like shell theory, is the transverse shear strains, which in a Kirchhoff-Love theory would be ignored. Kirchhoff-Love being analogous to Euler-Bernoulli beam theory, and the Reisner-Mindlin shell theory being analogous to a Timoshenko beam theory. So note that there is a gamma 1 and a gamma 2. Similarly, there is a K1 and K2, unlike in the case of a beam where you had only one of this and only one of this as well. Here you're having two sets of column matrices associated with the x1 and x2 directions, both of which are large. So now if you had not seen the edges very clearly, that's why I had this slide. So the schematic of the shell deformation in the undeformed state to the deformed state, starting with a reference surface over here, which is obtained by R from this point in the origin of the aircraft fixed reference frame, usually the CG of the aircraft. And then once you locate R, you're going to go x3, b3 along this and locate your R hat of a arbitrary material point P in the undeformed configuration. Now you want to track and get to that same point in the deformed configuration. So all that you're doing is to have the normal line element there undergoing three translations. Those three translations are accounted for in U, and once U is there, so you add to your small r, you add the U, you get the big R to locate the same point on the reference surface in the deformed configuration. But now you have to go along the B3 direction by X3, and once you go about that, you know that the normal no longer remains normal. It has become a curve and has become of different length as well, because of which you have three warpings. The change in length accounted for by W3, and the line to curve being accounted for by W1 and W2. In between, of course, you also had a rotation that is happening from the small b system to the big B system in introducing this big B1, B2 and B3. So let's just review that. So your R hat is now R plus X3 B3 in the small system, that is the undeformed system. Then you have the big R hat, which is now going to be not only R plus X3 B3 like in the undeformed system, but also the warping which is coming in. And the fact that we have a big R means that we have accounted for translations, and because we have the big B system, we have accounted for the rotations, and because we have Wi, we have accounted for the normal no longer remaining straight and having changed in size. Finally, you have, of course, these rotations that is an intermediate stage going from the small b to the big B system through the direction cosides. And then the same kind of notations we will use as we used in the beam problem. A tilde is basically to convert a column matrix into a square matrix. A 3 by 1 column, any 3 by 1 column matrix will become a 3 by 3 antisymmetric matrix by multiplying by this permutation tensor Eijk, which, as I said, has value of 1 when it is ijk, take on the values 1, 2, 3, 2, 3, 1 and 3, 1, 2. And if it is acyclic, it takes -1. If any one of those indices are repeated, it takes 0. So you end up with a 3 by 3 antisymmetric matrix over here. In other words, diagonal elements are 0, principal diagonal, and the other elements are consisting of the same elements as the column matrix, namely, let's say V1, V2, V3, but with appropriate signs. And like we were dealing with E1 in the case of beam, we need to deal with it here as well. In addition, we also need to deal with an E2, which is having the second element as 1 and the other two as 0. So this is again a column matrix because your transpose is there. It's written in a row form, but with a transpose. Therefore, once again, it's a column matrix. So now let's look at some glimpses of the variational asymptotic method for the shell or plate analysis. This is what leads to the Constitutive Law, in particular the relationship between the 2D strains and the 2D stress resultants. So in order to do that, we identified two small parameters over here. In the case of a plate, just the first one is enough, that is thickness to wavelength of deformation along either x1 or x2, whichever is the smaller of the two. And then we have also in a shell, the initial curvatures have to be such that the curvature is small, or in other words, the thickness is small compared to the radii of curvature. In other words, you're not dealing with things like shell which is folding around itself, etc., where the radius of curvature can be of almost the same order as the thickness of the shell itself. So as long as, but in such problems also you can break it up into two shells which are joined at that particular point and do a 3D analysis at that location where that curvature is taking place. So there are ways to overcome those kinds of complex situations as well. So an example is, for example, if you are looking at the airfoil cross section and you are looking at the trailing edge, you can see that the curvature is very large over there because it's turning around itself. Instead, you can deal with the top surface and bottom surface separately and apply the appropriate interface condition at the trailing edge in order to take care of that. Rarely is the entire airfoil analyzed as a single shell anyway. So then the thickness is of order h. Again, the actual thickness can vary along the surface as you go along x1 and x2. You can have different thicknesses, but essentially you are saying that the largest of them is still order h and is smaller compared to the other two dimensions which are of order L. So you can actually have different dimensions along this, which is the B and the L directions, breadth and length. But the actual numerical values might be different, but they are of similar orders of magnitude, and both of them are very large compared to h. So which is what your h by L is very small compared to unity indicates. So those are the geometric small parameters. In addition, if you had the strain as a small parameter, you can get an even simpler theory, but there are ways to relax this assumption also, even without this. For large materials which can undergo larger strain, like hyperelastic materials, there are ways of applying this same methodology, just that the number of terms to be retained become larger, and therefore the models become slightly more complicated, but still you get a computational efficiency over 3D models. So once these small parameters are identified, just the geometric small parameters alone, you can end up with a constitutive law and the appropriate recovery relations as the byproducts. So now we are in a position, we have gone through the flow chart, we have gone through the kinematics to look at the same parlance that we have looked at the 1D model, that is loads, stresses, strains and deformation as the variables, equilibrium, constitutive and kinematics as the equations which relate these four variables. So that's exactly what we would do. So we are doing a parallel to what we looked at as a geometrically exact beam theory. Now we are looking at a geometrically exact plate theory. So far in the previous two slides I was dealing with shells with initial curvature, but those equations will become very long and complicated, difficult to fit on a single slide meaningfully. Therefore I have specialized this slide only to plates. In other words, initial curvatures are not there, and which is a fairly useful problem as well when we are dealing with single panels between two stringers, or between a spar and a stringer, and between two ribs. Those wing panels are pretty much straight panels, except when you're dealing with the leading edge, etc., where you have to invoke the initial curvatures as well, which is also done, but we are not looking at it in our class. So it's a geometrically exact plate theory. Let's look at what are the variables which are involved. The 2D variables, very similar to beam theory, are the F and M, but now we are calling it Fi and M alpha, because there is no M3 that is involved over there. In other words, this particular moment, which is the drilling moment as it is called. You can understand the reason why it's called drilling, because what you do when you're drilling a hole into using a drill bit, let's say, and a drilling machine, all that you're doing is rotating to get into that particular hole, right? So that's essentially what's happening. But actual drill bit, even though it is smaller cross section, it is not zero cross section. Even a pin, if you use to poke, you are actually having, the pin is actually having a finite thickness or a finite diameter. So, but what we are dealing with here is a line, and a line doesn't have any finite dimension. It is zero thickness. Just like a point is having zero thickness, you are having the line also of zero thickness over here, and that's why M3 doesn't make sense. But as I said, there are director-based Kozarac theories where M3 is accounted for as well. And whereas all the three loads are possible as far as the forces are concerned, your F1, F2 and F3, F1 and F2 being stretching forces along the two directions, again distributed. Similarly, your F12 or F3 is basically nothing but your shear force that is there as well. And similarly, your M alpha. Or you could have the F3 distribution along the Q3 and introduce the loading for the shear in a separate way as well. So these are the applied tractions. These are not reactions. These are the applied tractions that you have on the surfaces. And in addition, you could have the body forces as well, and those body forces can be redistributed into these using the averaging out, or using the Green's divergence theorem, which can bring in the relationship between the volume integral and the surface integral. So we'll not look into those complications, but these are the resultant loads that are actually applied. It could be a lift distribution, it could be a drag distribution, it could be a pitching moment distribution, etc. So then how is the structure resisting that at the 2D level, at the surface level? So the reference surface level, it is resisting through these reactions, which are again forces and moments. Two types of forces are there. n alpha beta and q alpha, and one type of moment is there, which is the m alpha beta. What are these two types of forces that have resulted over here? One is the in-plane forces, and the others are the generalized shear forces Q1 and Q2. And n alpha beta involve n11, n22 and n12, all of which are in plane. n11 and n2 being stretching or contracting in the plane of the shell or plate, and n12 being shear within the plane of the plate. Whereas Q alpha is going to be perpendicular to the plate. Any shear which is acting perpendicular to the plate is going to be your Q alpha. So that these are reactions at that particular cross section. Now cross section means in this case, unlike a beam where we are talking of a planar cross section, here we are talking of a normal line element. And on that line element you also have your M11, M22 and your M12 taking care of the in-plane moments. That is basically you have, this is a plate, you apply a moment like this, which is going to at any location cause a reaction, which is basically sigma 11 multiplied by z, the distance from the neutral axis, integrated over the thickness. That is going to get a reaction. That is what your M11 is. Similarly, your M22 is going to be a reaction to bending which is applied in this direction. In addition, you could twist the plate, and when you're twisting the plate, there is a reaction that N12 can resist it with, and that's essentially when N12 is on the surface, but then tau 12 is also having a distribution above and below the surface. So tau 12 multiplied by the thickness or the distance from the reference surface integrated over the thickness is going to result in your M12, which is basically the reaction to a twisting moment which is applied. So you had an M3, M1 and M2 over there, and similarly you can have your F1, F2, F3 over there, and all those are going to be reacted through your N alpha beta, Q alpha and M alpha beta. Now that's as far as a statics problem is concerned. In a dynamics problem, you will have angular momentum as well, and you will also have the translational momenta P1, P2 and P3 about the x1, x2 and x3 direction. And here you see that there is a rearrangement which is made to make the equation simpler, to appear simpler. So the 1 and 2 are interchanged, and there's a sign also which is negative sign which is given to the first term, which is minus h2. But it's also interesting to see that there is no angular momentum h3 equal to 0. So there is no angular momentum about the third direction. Why? Once again, because the thickness is 0, there is no mass which is distributed away from that line, and therefore as far as the line is concerned, it cannot have an angular momentum component about its own axis. That's why your h3 equal to 0. There is only h1 and h2, which for just for purposes of simplicity in the equation or final expressions of the equations, we are going to interchange and change the sign. So then that is P and H, apart from N, Q and M. Those are all the 2D stresses. Not about the 2D strains. So 2D strains also you have in the statics and dynamic case. In the dynamic case, you would also have the velocity V1, V2 and V3 of that point, which is the intersection of the reference surface with the reference normal, and that in addition you would have the angular velocities, where a similar interchange is made between 1 and 2, but unlike h3 which was 0, omega 3 can be non-zero. So in other words, you can have an angular velocity associated with the third direction. It's just that you cannot have the momentum because there's no mass distribution away from the center line, which is because you're considering only that normal line to start, whose momentum you're interested in. So in addition to that, you have now your gamma 1 and gamma 2, which we introduced along with the kinematics, if you remember at the end of the previous slide, and then K1 and K2, which are involved with the reference surfaces curvatures along the various directions. But in addition, there's also the micropolar curvatures that you see in the third term over there. So K, alpha, J are the curvatures. So alpha takes on the values 1 and 2, J takes on the values 1, 2, 3. So there are essentially 6 curvatures, 2 into 3 over there. But K1, 2 and K2, 1 usually appear in pair as K1, 2 plus K2, 1. But for the purposes of the number of variables and the number of equations over here, let's keep them separate, K1, 2 and K2, 1. So essentially you are having 6 variables over there, the K, alpha, J. And similarly you have 2 epsilons along the alpha equal to 1 and 2 more epsilons along alpha equal to 2. There also alpha 1, 2 and alpha 2, 1 are equal to each other. So that is established through Lagrange multiplier, that the fact that the strain matrix is symmetric is taken into account by setting epsilon 1, 2 equal to epsilon 2, 1 through a Lagrange multiplier in the minimization of the energy functional or the action functional of the Hamiltonian's principle. Finally, we have the deformations, which are the 2 sets of quantities, u and theta, which are going to be over here. That is, u is a function of x1 and x2. Similarly, your Cij is a function of the thetas, which in turn are a function of x1 and x2, which are the 2 variables about which the rotations can happen. And once again, the direction cosine matrix is a dot product of the 2 sets of unit vector systems. So then, now we bring in the relationships between them, which are start with the equilibrium equations. So these are the equilibrium equations. Once again, ordinary differential equations, if you are taking in the case of the beam, but here in the case of a plate, you are having, even in a statics problem, 2 independent variables spatially which are along the reference surface, which are your x1 and x2, and therefore you will have partial differential equation even in a static plate problem. And that's why you see derivatives with respect to not only x1 but also with respect to x2. And this artistic n that you see is the one which is the Lagrange multiplier for setting that epsilon 1, 2 equal to epsilon 2, 1, as I said in the previous case. And that is also obtained when you are minimizing with respect to the Lagrange multiplier, the entire functional. You can solve for n using this particular equation, which can then be substituted. This equation 1 can be substituted wherever this n is appearing, which are those 2 places, as well as over here. Okay, so essentially there are only 5 equilibrium equations corresponding to 3 force equilibrium and 2 moment equilibrium, because as I said, there's no moment about the drilling degree of freedom, so there is no equilibrium equation associated with that as well. So essentially there are only 5 equilibrium equations that you have associated with this. Next, we go on to the Constitutive Law, which is where you see you're familiar, for those of you who are familiar with analyzing composites, you know that the classical laminated plate theory has this matrix of A, B, B and D. So that's what you see over here, with the twist that they can be functions of the 2D strains, which are listed over here: epsilon 1, 1, epsilon 2, 2, epsilon 1, 2, kappa 1, 1, kappa 2, 2 and kappa 1, 2 or kappa 2, 1, which are contained within this big K. Big K having the initial curvature and twist as well, but because here we are dealing with plates, big K and kappa are one and the same because there is no initial twist and curvature. So your big K itself becomes your 2D strain. In addition, you also have now the shear forces Q1 and Q2, which are related to the transverse shear strains. Transverse shear forces are related to the transverse shear strains through another matrix which we call as the G matrix, which is also symmetric. Then this is as far as statics is concerned. Once you bring in dynamics, which is when the right side of the equilibrium equations kicks in, so these terms would have been zero in a statics problem, but in a dynamics problem you have translational momenta, angular momenta. Samanvai, go ahead.
Sir, in this question, the forces should also be there now.
Which case?
F1, F2, N1, N11, N22, N12 equal to this constitutive matrix into strain plus forces should also be there now. F1,
that's correct.
F2,
that's correct.
F3.
Yeah. So that's what is your N. So the N system.
Tractions.
N's are the tractions, and what is applied is your F11, F1, F2, F3 over here, and your M1 and M2 over here, which are applied. Okay. So you will see them exactly in the same locations where you saw in the beam problem. So Renuka, I already mentioned in the beginning that this class will continue even after the students leave, as the recording will be made available on YouTube as well as, of course, on Teams platform. So I'm going to continue to finish this because we missed the previous class, and the coming Thursday is a holiday, so we cannot have a separate class. So that's the reason why I'm completing this. So it will not take much longer, maybe another 15-20 minutes we should be done.
Okay, sir. Okay.
Yeah. So I had in fact allowed the students to leave as and when they want, whenever they have commitments. So you also, if Renuka and Rajesh, you need to leave for your lunch, which probably is already quite late. So please feel free to do so because this recording will be available and you can always watch it later on. So coming back, so those are the constitutive laws, N and M related to epsilons and Ks or kappas, and your Q's related to gamma. That's all that is necessary in a statics problem. But in general, we have a dynamics problem. So we bring in the translational momenta and the angular momenta, how they are related to the velocity and the angular velocity. And that is through the mass per, and these integrations here, the angular brackets have a different meaning over here compared to the beam. In the beam, we were integrating over the smaller dimension, which means the entire cross section. So it was an area integration. Here we are integrating over the smaller dimension of a plate, which is the normal, which is therefore just a line integration over x3 equal to minus h by 2 to plus h by 2. So all these angular brackets that you see over here, here and here are all integrations over x3 over the entire thickness of the plate or shell. So now, so if you are integrating the density of the material, for example, and it could be different layers, could have different materials. So you're integrating all of that over each layer and then adding up over all the layers to get this mu. So you're integrating rho, which is a mass per unit volume, over the thickness. So you end up getting mass per unit reference surface area. So mass per unit area, unlike in the case of a beam, you are dealing with a mass per unit length along the beam. Here you're dealing with a mass per unit reference surface area about the as the terms which are going to affect the translational momenta, how it is going to relate to the velocity. Similarly, you're going to have the moment of inertia, which is going to depend upon the same mu, and your r squared, which is going to be given by a mu r squared, is equal to an integration of the density weighted with an x3 squared by going to the location of that particular material point whose densities you are considering. So that's essentially the definition of your inertial moment. Once again, you see the third element over here is actually 0 because you do not have any distance at which the material is located on the normal line element itself. So whatever we are dealing with here is for the normal line element, just like in the case of the P and H and V and omega of a beam, it was that of the cross section. It's a translational moment and the angular moment of the cross section. In other words, for the beam as a whole, it's per unit length. Here it is per unit area that we are dealing with, and therefore it's of a unit normal, the translational momenta and the angular momenta that we are considering here as P and H. Then there is one more term which brings in certain off-diagonal terms. If you are not considering the reference surface as the mass centroidal surface, in other words, you have taken the, let's say, the mid surface, but the kind of materials on the top and bottom are different. So you are having going to have this CG location not at the reference surface but slightly higher or lower. So that's essentially what is going to bring in an integration of x3 into rho over the thickness, non-zero values, and therefore you're going to have a mu xi bar, and then you put that into the tilde matrix, the antisymmetric matrix, and then you end up with these two coupling terms. Otherwise, the translational momentum will depend only on translational velocity. The angular momentum will depend only on angular velocity. One is through the mass per unit surface area, the other through the moments of inertia. But once you have the reference surface different from the mass centroidal surface, then you are going to have the coupling happening, translational momenta depending on angular velocities and angular momenta depending upon translational velocities. Finally, we have the kinematic equations. The kinematic equations are going to relate the 2D strains to the 2D deformation. The 2D strains are gamma alpha and k alpha in the statics problem, and in addition V and omega in a dynamics problem. The deformation is in terms of u and theta, both of which again functions of only x1 and x2, and that's what you see over here, the derivatives of u with respect to x1 and x2, and the derivative of u with respect to time. Similarly, the rotations theta, instead of explicitly putting them, we have put in terms of the direction cosine matrix into which theta are contained as cosines of those thetas, and therefore we have a C over here, a C comma alpha, which is C comma x1 and x2, which is the coordinates along the reference surface, and then a C which is dotted as well, which is a derivative of containing the derivatives of the thetas with respect to time. So, and in addition to those, we also have the velocity of the aircraft, small v, and the angular velocity of the aircraft because of its pitching, rolling, and yaw, which are coming in as well into this overall system, because we are referring to an inertial frame of reference, which is an earth-fixed reference frame of system. Only then the equations of motion and many of the kinematics will be valid, and that's why we are bringing in that, because the aircraft itself may be accelerating. Once it is rotating, obviously there is acceleration. Even if it is not rotating, it could be accelerating either through a climb or through a cruise velocity, which is changing to a different velocity. So that's essentially what you're seeing over here, and once again you will see beautiful parallels between what k is doing and what omega is doing in a spatial sense and a temporal sense, etc. The kind of analogies that we discussed in the beam problem. So I'm not going to repeat that over here, but you can very clearly observe that whatever prime is doing for space, dot is doing for the time derivative, but just that prime has now been replaced by two derivatives. One is with respect to x1, other with respect to x2, what we together call as comma alpha. So comma alpha and dot are going to behave very similarly with your curvatures and with the angular velocities respectively. So that's as far as the kinematics are concerned. Finally, here also, with just that alone, you have the geometrically exact plate theory. And if you bring in initial curvatures, you can have the geometrically exact shell theory as well. But we are not stopping there. We know that as far as the differential equations are concerned, it's quite simple. They are partial differential equations, but the level of non-linearity that is involved is once again quadratic. You see k multiplying n over here, etc. Q multiplying epsilon. Many other places you can see omega multiplying p, or omega multiplying h, v multiplying p, etc. But all the non-linearities are quadratic, except when you come to c. And once again, the rotation is the culprit, which is bringing in an infinite level of nonlinearity. So if you want to reduce that nonlinearity also to a second degree of nonlinearity, that is quadratic, we go to a fully intrinsic formulation where we get rid of 2D of deformations totally. We don't need all of these kinematic equations. To do that, we are going to do something very similar to what we did there. In other words, we have to take the comma alpha derivatives of velocity and angular velocity, that is, take its derivatives with respect to the reference surface coordinate curves, and we are going to take the time derivatives of gamma and k tilde or k alpha, which is going to result in elimination of c as well as u, so that you don't need any displacement or rotation variables. You can just directly relate gamma dot and k dot to v comma alpha and omega comma alpha, which is what we will do now. So we are bringing in the fully intrinsic geometrically exact plate theory. So you're further qualifying the geometrical exactness by eliminating the displacement and rotation variables. And to do that, as I said, you take the derivatives of velocity and angular velocity spatially and the 2D strains temporally, and then you relate them by eliminating c and u. Once you do that, you get this beautiful set of equations which are just having only first derivatives. Even here you see that only the highest derivative that you have in the equilibrium equations are also first derivatives. So though they are partial differential equations, nonlinear up to the quadratic level, but they are all ordinary differential equations. Even here in the time you see there is only the first derivative which is involved over there. So you see that in addition, now the fully intrinsic equations that you got as a replacement for these two sets of equations are going to be first order differential equations as the previous ones were, but the only advantage that we are getting is that we have got rid of c and theta, and therefore we are having at the most quadratic nonlinearities through this v tilde k alpha term and the omega tilde k alpha term, as well as this omega tilde gamma alpha term. So here once again, someone where you would see that there is an addition not only with E1 but with respect to E2 as well, because you're going to have the gamma 1 and the gamma 1 and gamma 2, which are nothing but the extensional strains along the surface in the 1 and 2 directions, which have to be with respect to where they originally were, and that's where the 1 is coming as the source over there. So that's going to multiply by omega tilde to contribute towards a v comma alpha. So then once we bring in this fully intrinsic equations, we have no longer a need for the deformation, that goes away, and the kinematic equations go away as well. Now these are the three sets of equations that we deal with. The equilibrium equations here, the constitutive law over here, of course both these sets, the statics and the dynamics, and then in lieu of the kinematics we have this set of fully intrinsic equation, so that you have a complete set of equations, a boundary value, initial value problem combined over here, involving once again differential equations, first order differential equations, and algebraic equations which are coming from the constitutive law, which in general can become nonlinear by bringing in the dependence of epsilon and k into this when you have very thin shells or very thin plates. So I think with this we have completed this shell or plate theory as well. If there are any questions on this, I'll be happy to answer. Samanvay, Franklin, Subhashish, and a few others were there.
So this equation for the fully intrinsic one, we did it by differentiating with respect to time. for the gamma alpha equation, that was C under bracket E alpha plus U comma alpha minus E alpha. By those equations we got this.
Yeah.
Okay.
Right. So all that you're doing is you're taking these two, which are basically velocities, you're taking a spatial derivative, prime. And these two, which are strains, which are actually already having the spatial derivative, you're taking the dots, which is the time derivative. And between them, you are once you do that, you have to do a little bit of algebraic manipulation to eliminate all the C's and the U's. So once you do that, you end up with this equation. So it's just the equivalent of those.
Means we don't want the equation to be function of displacements and rotations.
Exactly.
Okay,
That's right, yeah. Anybody else? Any questions? Okay. Okay, so we had a glimpse of the 1D and 2D theories, the state of the art. We'll finish the last 5 minutes with the 3D elasticity in the exactly same framework. So, in other words, you have 3D, all the loads, stresses, strains, and deformations. Those are the 4 sets of variables. And then you have the 3 sets of equations, equilibrium, constitutive, and kinematics. In beam theory, we had it as 1D. Plate theory, we had it as 2D. Now we are having it as 3D everywhere. So all these terms are 3D quantities. That's the only difference. So now, what are these? These are things that you're very familiar with. In the case of the 3D loads, you have the tractions. So you have any arbitrary 3-dimensional body that you have. Then you're applying on the surface. There are certain forces which are called as the tractions. And then there is a distributed force within the body, which is your body force. You can either express it per unit mass, in which case you have to multiply by the mass density, or you can express it as per unit volume. So let's take it as Bj. In examples where it's given as per unit mass, remember to multiply it by density, mass density, so that it becomes per unit volume. So these are the applied loads, Tj and Bj, where J takes on the values 1, 2, and 3. Next, we have the next set of variables, which are your stresses, which are your sigma ij. And there are very many different definitions of the stresses. Here we'll take the nominal stress, for example, or the first Pyrrho-Kirchhoff, which is not symmetric. Then you would have to include additional equilibrium equations from the moment, which say that the sigma ij and sigma ji are related to each other through the deformation gradient tensor or whatever. But if you take a let's say a set of stresses which are symmetric, then you have the moment equilibria already satisfied in problems where the materials are not having any body moment distributions. So let's deal with the second case, the simpler case. So sigma ij, set of symmetric elements. Then we go on to the strains, which are big gamma KL as distinguished from epsilons, kappas, etc., which we were dealing with as 2D or 1D variables, which were functions only of x1 or x1 and x2, not of x3 in the case of the plate or shell, not on x2 and x3 in the case of the beam. So here they're going to be functions of x1, x2, x3. That's why you're using just a different symbol here, big gamma. In lieu of sigma, of course, you had n and n, m, q, etc. in the case of plate or shell theory, and you had f and m uppercase in the case of beam theory. So that's as far as 3D strains are concerned. Finally, we come to the 3D deformation, which is your U. That is once again U1, U2, and U3. So here we are talking of a point. Therefore, there's no rotation involved. We're talking of a body, but we are talking from point to point what is happening, and a point doesn't have any rotational motion. Just like a line didn't have a rotational motion about one of the directions, a point doesn't have rotational motion about all 3 directions. There's only thing is U. So it looks very straightforward and simple in terms of the variables. It will look very simple in terms of the equations that you are going to discuss as well. But the complication comes because you have an additional spatial direction or 2 additional spatial directions going from either a shell or a beam to a 3D model, and therefore the the nature of the partial differential equations becomes far more complex, even in the case of statics, leave alone dynamics, when time is a fourth independent variable. So what are the equilibrium equations? You are very familiar with this. It's the divergence of the stresses which written in a Cartesian coordinate system just becomes sigma ij comma I, where there is an implied summation over I equal to 1 to 3, and then you are subtracting the body force per unit volume. Then you would have got 0 if it is a static problem, but now because it's a dynamic problem, it's equal to the inertia force per unit volume, and that inertia force per unit volume is the mass per unit volume, namely the density, multiplied by the acceleration, which is uj double dot, coming from the u that we introduced as the 3D deformation field. Then in addition to these, which are satisfied at all the interior points, at those of the exterior points at which the traction is specified, it's not the entire surface at which the traction will be specified. There are certain subset of the entire boundary surface where the traction is specified, and that is Tj, and therefore the stress has to be equilibrated to those tractions at those locations, where we introduce n as the normal to the surface at which the traction is specified. And once again you have this Ei, which is basically 1 0 0 for I equal to 1, 1 0 1 0 for I equal to 2, and 0 0 1 for I equal to 3. Remember that we needed only E1 when we were dealing with the beam. We needed only E1 and E2 when we were dealing with plate. Now we are dealing with shell, with the 3D body, we need all three. That's why Ei. So those are the boundary conditions. Those are the natural boundary conditions or the traction boundary conditions. So that constitutes the equilibrium equations. Next we go on to the constitutive law. The constitutive law for a green elastic material as opposed to just a quasi-elastic material. A quasi-elastic material will give you sigma as a function of gamma. It will not tell you what kind of function it is. It may not be a linear function. So once we bring in a linear function, first of all by bringing in all those symmetries, which is basically why sigma ij is equal to sigma ji, the symmetry in the stress matrix through the absence of the body moments, you move from a Cauchy elastic material to what is known as a green elastic material. Now a third level of approximation, a Hookean elasticity, because it is linear also. One, sigma is a function only of gamma. That is called Cauchy elastic. Then sigma is a function of gamma, but sigma is symmetric because of absence of body moments. Then you have a green elastic material. Then you move on to a situation where not only you have Cauchy and green, but also a linearity between stress and strain. You have Hookean. So Hookean elasticity is a subset of green elasticity, which is a subset in turn of the Cauchy elasticity. So there you have written again in a Cartesian coordinate frame, gamma KL multiplied with Eij KL, where there is an implied summation over K and L to result in the stresses sigma Ij. So finally you have the kinematic equations, which relate the 3D strain gamma to the 3D displacement or deformation u, and that is what you have over here. So if it was a geometric linearity, you would have only these first two terms, but because you have a non-linearity, you have this additional quadratic term as well. Now this is green strain or green Lagrange strain, but you can have various other definitions of strain. Once you change that definition of strain, you will change the corresponding definition of stress, so that the overall relation between the tractions and body forces on the one hand and the displacements on the other remains 1:1. So that you have, if you change sigma, you have to change gamma as well appropriately. So for this choice of sigma, we have this choice of gamma over here, and that's why you have this particular definition of the gamma in terms of the displacement field as well. In addition to this, which is valid at all points, all material points, you have the boundary conditions. Just like here we had the traction boundary conditions, or what are known as the natural boundary conditions. Now we have the boundary conditions which are associated with the geometry, and therefore known as the geometric boundary conditions, which specify either the displacements or the displacement between 2 points, wherein you bring in the rotation in a different way. So when you're talking of points, you can't talk of a rotation. When we are talking of a derivative over here, which are dealing with 2 separate points and how the translation has taken place between them, then therefore you bring in an m comma l, you can specify certain rotation kind of boundary conditions here as well. But in most situations, this should suffice. But if the problem is defined in such a way that certain rotations are also mentioned at certain location, certain line elements or surface elements of the body, then you have to invoke this as well in addition. So that concludes this whole discussion on the equilibrium equations. Once again, you see these are partial differential equations of the first order, but because of the double dot over here, because we didn't introduce an intermediate momenta, therefore the second order differential equations are coming. But you can do the same thing that we did with the previous 2 examples and introduce the translational momenta P over here, in addition to sigma as the 3D stresses or generalized stresses in the temporal sense. Then you can avoid this double dot or double derivative and deal with ordinary differential equations here as well. Then you also see that algebraic equations are coming over here, and if you had an hyperelastic materials, then you would deal with the fact that your Eij KL is no longer constant. It is going to be a function of gamma KL, and therefore you need to take that into account as well. In other words, you no longer have a Hookean elastic material. Finally, as I said, you can have many other definitions of strain which can further complicate these things, but they might be simpler to deal with when you're dealing with certain specific kinds of materials. So finally, whether you're dealing with a 1D model, 2D model, or a 3D model, the eventual implementation is going to be using a finite element analysis for a complicated structure, using 1D finite elements, 2D finite elements, and 3D finite elements, and most of which is done using commercial software like Abacus, ANSYS, Nastran, LS-DYNA, IDEAS, FEAP, etc. There are also software associated with the variation asymptotic method, like the VABS, for example, VAPAS or VAMUCH for different geometries, VABS for beams, VAPAS for shells and plates, and VAMUCH for the microstructural analysis, micromechanics of various kinds of microstructures that you might have both in metals as well as composite structures. And then you could also have these 1D and 2D done in a geometrically exact fashion, what are known as GBT, geometrically exact beam theory. There are codes associated with it like Natasha, Comrade, etc. And then you can basically combine them with these overall 3D finite element analysis because there are very good interfaces between them as well. So once you have all of these, you can do anything which is structural aeroelastic analysis, dynamic analysis, aeroelastic analysis, etc. And essentially within these software, you have an inbuilt boundary value problem or an initial value problem to which you feed the appropriate boundary conditions and then let the computer program itself solve this. So when you're doing that, you have to be very careful. So the role of the engineer is very important. Otherwise, you end up with a garbage in, garbage out. So the proper inputs, the proper selection of the elements, the proper utilization of the end results in post-processing and interpretation of them are all very critical. So therefore, the major modeling tasks that are involved for an engineer today, unlike in the past, are basically to apply this particular software appropriately. And once you do that, you need to, even before that, understand clearly what is the purpose of the analysis or design problem that you're doing, and therefore focus on those aspects which are essential, so that it's not a donkey work which is being done, which is done in a much more intuitive and intelligent fashion. And once you do that, you can simplify the system into the 1D or 2D models without sacrificing the required level of fidelity. So when you go from a 3D finite element to a 2D or 1D finite element, there is going to be a drop in accuracy, but a huge increase in computational efficiency. So if you use the right kind of 2D and 1D models, then the drop in accuracy will be almost negligible, but the increase in efficiency will be tremendous. And that's why you try to simplify the system through this dimensional reduction. And the dimensional reduction is something that is not only from 3D to 2D or 1D, but in a more intricate sense, from an n-dimensional sense, to a smaller dimension, n-1, n-2, n-3, etc., all the way to a 0 dimension as well. So there's a lot of philosophy which goes into this, where you move either through a dimensional reduction to nothingness, or through a dimensional expansion into everythingness, which basically is also all about life as well. So once you understand these things, moving from a 3D to 2D or 1D or vice versa, you can very easily see that dimensional reduction or dimensional expansion can be applied to various other problems, not only of engineering but of life itself. So coming back to the finite element analysis, what we do next is to provide the input data on the dimensions, on the material properties, and on the loads which are applied, which essentially are used as some of which to modify the governing differential equations, and some of which to modify the boundary conditions and or initial conditions. Then once you end up with the results that the commercial software throws up at you, you have to judge the correctness of the result. So this judgment is a very important, crucial functionality of us, the engineers. Then we have to interpret the physical relevance of those results, what it actually means into the actual physical problem. Because the reality is a physical reality which you have used a model for, and a mathematical expression, which in turn into a computational algorithm and a computational implementation into a code. And that code has given you results. You have to work backwards towards the physical reality to make the interpretations of how those results are relevant. And eventually, if it's a design problem and you have done it as an analysis, because most of these software in the way they are, without any user subroutines, they are predominantly analysis software. So if you're using it for a design purpose, then this analysis has to be into a loop, an iterative loop of optimization towards the design. So there, at each end of each converged step, you can make certain design changes to make it a better or closer to optimal design than what you started off with. So essentially, in this whole process of 6 steps, you see that it's not only science and engineering, but there's a lot of art involved as well. People talk of STEM as something important, science, technology, engineering, and math, but it's moving slowly from STEM kind of paradigm to what is known as STEAM, STEAM, where this A is standing for the art that is involved in this whole process. Otherwise, you end up doing donkey work. So that's when you use both your left and right brains appropriately in a balanced way, and bring in the art into the science and engineering. And that's where once we automate all of these things, further bring in artificial intelligence, machine learning, etc., so much of what we used to do normally as a human being, as individuals or as teams, are now being done predominantly by computational algorithms and computing systems. Therefore, our role is becoming more in terms of what we feed into them, and how we take what are the outputs, and then how we interpret those outputs. And there, this A plays as critical a role as the STEM plays. So that's the reason why you have to focus on the artistic aspects as well, to have a complete understanding of not only structural dynamics and mechanics, but of life itself. So with this, I will conclude with a few parting thoughts that we complete this course, Flight Vehicle Structures, which was basically an introductory course, but there's a lot more to be done beyond this. But I try to give, even in an introductory course, a flavor for the state of the art, primarily because I want this to be a real takeaway for the physical situations that you're going to deal with as actual aerospace engineers in the industry, or even in academia as researchers, to do meaningful research rather than just incremental improvements over whatever is already there. You can do substantial improvements if you have this overall understanding and the state of the art as well. So I wish you the very best in taking off and climbing in the very parlance of aircrafts. Not only in your education, many of you are starting with PhDs and or masters, but also beyond that towards your career, and also life in general needs to take off and climb. And such an evolution is possible only when you are always on the cutting edge, dealing with the state of the art, at the same time looking at the bigger picture to see where what you are doing, where it will eventually fit in. So once you are satisfied in doing these two, you can, whatever contributions you make towards engineering and towards the society can be of substantial value. So thank you very much. I have enjoyed teaching these 26 classes. I hope some of you at least enjoyed at least in a fraction of what I enjoyed in teaching this, because I think of this not as just a course, but as a big stepping stone towards how you deal with engineering in particular and life in general. Thank you very, very much.
Thanks a lot, sir.
Thank you. Thank you, Subhashish. Thank you, Samanbhai. Keep in touch, and we can discuss many of these things later as well.
Yes, sir. Sure, sir.
Okay. Bye-bye.
Thank you, sir.
Thank you.
Sir, one doubt regarding
Yes.
the exams.
Yeah.
So, how we are gonna have some exams?
Yeah, so it's going to be an open book, open notes, open-ended exam in the sense that it's not like a 3-hour exam, though it's an exam that can actually be done well within 3 hours if you're familiar with whatever has been taught. I'm just giving you a more realistic situation how you typically face in the industry. You rarely get a deadline which is of 3 hours, and rarely get a problem situation where you're not allowed to consult books and notes and lectures and videos, etc. So here you have all those available to you. You will have about a week to submit your exam. So most probably I will be uploading the exam by this Thursday, and so you will have the Thursday after that, that is on the 14th to 21st, by which time you can submit your solutions. And again, I'm not precluding any discussions between yourselves, etc. Feel free to discuss if necessary, because the whole purpose of an exam is also to enhance your further knowledge. So feel free to discuss, etc. if you need to, and then submit your just like how you submit your assignments, you submit your exam as well, and that will be corrected on time. But please don't delay, unlike some of the assignments some of you had delayed in the past. Please don't delay this submission by Thursday, because the corrections have to be done for all the nearly 40 students by the teaching assistants and me, and then the grading has to be done, and the grades have to be submitted with a strict deadline. So please, I request all of you to do that. In terms of what you would have in the exam, it's entirely based on what has been taught through the entire course, but especially in the last 2 classes will play a critical role in terms of the overall understanding of these concepts, not in terms of solving these complicated equations, etc., which are typically done by computers. So you have access to these equations, but you should know what is the meaning of all those variables that are involved, what are they functions of, what do they, how they correlate to in a real life problem, not only in a typical beam or shell, but also in the case of an actual flight vehicle component like the cover skin or the spar or stringer or a bulkhead or a rib. so how they correlate with those things. So most of the questions will be objective type. Many of them will be multiple choice questions where more than one answer can be right. But not only do you need to choose the right answer, but you need to explain why that is a right answer and why the others are not right answers. So it will be an objective type with a twist to have an explanation, and those explanations should not be long drawn paragraph level explanation. At the most, 1 or 2 sentences will be sufficient to explain all of them, and then in addition to that, you will have 1 or 2 problems which will be a little more involved than the objective type, but again based on all that we have done over here, just taking it one step further. And so that's essentially how it's going to be. So please request all those who have missed this class also to see this video till the end, so that they get an idea of how the final exam is going to be. But in any case, within 2 days you are going to actually have the question paper in your hand, and so there's not much advantage that you guys who are staying back over here to listen to me are getting over those who may not have heard this. Is that fine?
Yes, got
Okay. Okay, welcome Bharat. So if there are no further questions, we will end the class here, and hope to see at least some of you in some of the future classes that we take. And even if you don't meet in formal classes, you're always welcome to consult with me whenever you have any doubts related to flight vehicle structures or anything in general in aerospace. Thank you very much, and wish you a great time. Bye-bye.
Thank you, sir. Bye, sir.
Thank you, sir.
Welcome.
Thank you, sir.
Welcome. Bye-bye.
मृत्युंजय मंत्राः
त्र्यंबकं यजामहे सुगंधिं पुष्टिवर्धनम् उर्वारुकमिव बन्धनान् मृत्योर्मुक्षीयमामृतात् एते सहस्रमयुतं पाशा मृत्योर्मर्त्याय हन्तवे तान् यज्ञस्य मायया सर्वान् वयजामहे मृत्यवे स्वाहा